Oh, get all these people. Hello.
Hey.
Afternoon.
Afternoon. Oh, Moshe, I like your vest.
Thank you.
Yeah, perfect weather for that.
How are you doing?
Pretty good.
Good.
All settled in your new home? After the move?
I heard new home. Looks the same though.
Oh, yeah. Well, it's a long story.
Are you still in South Jersey?
My ancestral home. Yeah. Yeah, South Jersey.
That's your ancestral home? Are you Native American?
Yeah, what was Elizabeth Warren say? Just a bit.
The Schmohawk Indians, I believe, live in South Jersey.
Yeah, I forget. I think, well, there's a couple things around us named after, at least in the town over, like Lenape. I think that maybe was one.
Oh yeah, well the entire Northeast has, Native American names. I grew up in Canarsie, which is Native American. But you may have heard of the Fugawi tribe. Has anybody heard of the Fugawi tribe?
No.
They would always get lost trying to navigate the terrain. And they would always say, "Where the fuck are we?"
Dun, dun, dun.
Nobody heard that joke?
That's
It's like
good.
a junior high school joke.
I didn't go to high school here. I'm not a native, okay?
Yeah, it loses in the translation.
I'm told that Hoboken is also an Indian name.
Well, everything, Munachi, Hoboken.
I always love that, like in a little bit upstate New York, there's that place, Hohokus or whatever. I thought that was
Oh, yeah.
Indian.
Rockaway. Rockaway is actually an Indian name.
Oh, really?
Rockaway. Yeah.
Huh.
Rockaway.
Really?
Yeah.
What?
Well, are you from Rockaway, Marty?
But I would think it meant rocks or something.
No, well, I mean, it sounds like it could be English, but it's actually a Native American name.
Huh.
But Lenape, yeah, Lenny Lenape were the tribe that
In Belgium.
around New York.
So, yeah, is everybody doing good? Yeah, sorry we didn't have a meeting last week. It's been a little busy. But yeah, it'll be fun to do today's meeting. You know, I actually wrote it way back in May, I think. We just never got around to it. It'll be fun to return to this wormhole stuff after some.
So can I ask a preliminary question?
Yeah.
The only possible Majorana fermion of which we may be aware is the neutrino. So are you going to get into any of that, or are you proposing other exotic particles?
Yeah, is the neutrino at Majorana?
I mean, if there are right-handed neutrinos, which have not been discovered, we only know of left-handed and right-handed antineutrinos. But if there are right-handed neutrinos and left-handed antineutrinos, they could be Majorano fermions. But as far as I'm aware, there are no other candidates.
From what I know, and actually this is not a subject I know all that much about, like when people, kind of engineer condensed matter systems to have this thing, the SYK coupling. Like, I'm not actually sure what they make them out of. It's actually a good question. You'll see it like similarly to the qubit model, it's like the sort of implementation details are, don't really affect like the sort of nature of the wormhole protocol, like, so to speak. The thing about, it's a good question.
Can I ask you
Like, in a way
something
we-
about the qubit model that you talked
Yeah.
about? I probably fell asleep during that lecture. I don't know, it's past my bedtime. But, you know, quantum teleportation is not like Star Trek teleportation.
Yeah, that's true.
Quantum teleportation does not happen faster than the speed of light. You have to transport a classical bit in order to figure out the quantum bit,
Yeah.
or
Although
vice versa. So,
it's
whereas a wormhole happens instantaneously, doesn't it?
well, I mean, even with quantum teleportation, you know, like maybe we should draw out the diagram actually.
In quantum teleportation, the only thing that gets transported is information.
Yeah, but it can't be at the speed of light. I mean, you still have to transmit information classically in order to supposedly correspondingly transport quantum information at the same time. But nothing happens instantaneously like,
That's true.
Yeah.
It is not instantaneous.
yeah.
I don't know if you guys can see this. I maybe I should draw this like a little.
Because everybody has teleportation and they think of Star Trek,
So
which also was probably not broadcast in Israel, or was it? Did you get Star Trek in Israel, Moshe?
When I was a kid in Israel, we did not have television, point.
And you know, everybody on Star Trek was Jewish except Sulu. Leonard Nimoy was Jewish. Shatner was Jewish. I think Sulu converted later in life.
so the thing about
Anyway.
so you know this is a good point about quantum teleportation. Like I would say there's like sort of like there's to some extent you can think about it like as being sort of instantaneous, like so to speak. So you know, to draw it out like in the string diagram way, you have here a wire, and so like if we're gonna just do like one qubit, you know, your qubit state's you're gonna plug that in there. We have this cup, which, as you recall, represents like a maximally entangled state of 2 qubits in this formalism. And the idea is like we have, you know, the qubit we want to teleport coming in. We have 1/2 of the entangled pair. They come in here and we do a Bell measurement. So
Well, one half goes to Alice and one half goes to Bob.
yeah. So this is like
That's how so Alice and Bob are entangled in that way. Yeah.
and this is Alice.
Well,
And,
I think Alice, I think typically sends the.
oh, okay. Well, yeah.
Okay, whatever. Yeah. Okay.
Okay. Yeah. Well, it's true. A and B. I mean, I guess A should be on the left. I mean,
Yeah.
we are.
But Alice has to do a measurement.
World.
Alice has to do a measurement before
Right.
she can Yeah. So one.
Yeah. So Alice does this measurement, and it's, you know, you can sort of formulate this in different ways, but like the usual thing is say, oh, it's a Bell measurement. So, you know, it could be 1 of 4 states, and you get 1 of the 4 Bell states.
Right.
You know, either like the, you know, 1 0 plus 0 1, or 1 0 minus 0 1, 1 1 plus 1 1, or 0 0, 1 1 minus 0 0. One of those 4.
What is a Bell measurement?
Sorry, say it again.
What is a Bell measurement? What is a Bell measurement?
Well, those are the Bell states, Moshe.
Yeah,
The
so
4
it's
states.
Yeah,
like a joint measurement.
What does she measure?
So one of the ways to implement it is to do like a, you know, like when we talked actually last time about the variational quantum eigensolver, we saw how we could implement kind of like an arbitrary measurement using Z measurements. So, you know, one way that it's often formulated is like you'll do, you know, some stuff like a Hadamard and a C naught or whatever, and then measure the 2 qubits in the Z direction. And
Can I say something, Matthew?
Mm-hmm.
One moment. By Bell measurement, you mean she measures the combined state, but not the individual states?
Yes.
That's not what she does.
Well,
What
no,
she does.
if you formulate it that way, yeah, it's a joint measurement on the 2 qubits, and it leaves the 2 qubits in one of these 4 entangled states, you know, which are orthogonal.
Matt, let me just,
So again, one moment. Again, she measures the total spin of the 2 qubits without measuring the individual spin of either qubit.
Well, it's not exactly the total spin, in the sense that, I mean, I guess both of these would have total, like all of these would have total spin 0 or what, well.
can I clarify something? Because I think I understand this.
Okay.
What happens is you create a Bell state. You create a Bell state, one of these 4 possibilities. Then she makes a measurement and transmits that measurement as a bit to Bob. And then from that, he can figure out what the original state was.
Okay, if I'm taking a peek at Alice's laboratory to see what she's doing, what is she measuring? She starts again with 2 particles in a Bell state, completely entangled. She sends one of them to Bob. She takes the other one. She combines it with the qubit that she has, and she does a measurement. What is the measurement that she does experimentally, operationally?
She does
What
one
does
of
she do?
4. She does one of 4 possible measurements. She does a not.
No. It's well, there's 2 ways of thinking about it. Like materially in a lab, like I don't know how to make a so-called Bell measurement. Like I just don't know the specifics of it. But you know, it's one measurement that has 4 possible answers. So there's gonna be some operator, and these are gonna be the 4 eigenstates. But you can reformulate it as just a unitary operation on these 2 qubits, followed by 2 separate Z measurements. So like one way of thinking about it, like for example, from the Wikipedia article is, let's see, wait, let me share the screen a bit, is here. So in this diagram, the 2 phi's are the initial entangled state. C is the qubit coming in. And you do a C naught on the qubit coming in and the first entangled pair, and then a Hadamard on the incoming qubit, and then you do 2 separate Z measurements on these 2 guys. And so you get 2 bits from that. And so those are the 2 bits that are then sent over here. And depending on which of the 4, results, Bob does one of 4 like correction operations.
One moment. So altogether, Alice is going to send 2 bits to Bob.
Yeah.
One is the measurement of the spin in the Z direction after it has incurred C naught. The other one is a measurement in the Z direction after it has been rotated by 45 degrees. So certainly the second measurement after the Hadamard is not going to tell you what was the initial state.
Bob has to decode it. Bob has a circuit that decodes it. He has the opposite.
No, let me finish.
Yeah.
Don't interrupt me. The point is that after going to the Hadamard, the initial state of C does not exist anymore. It has been erased. There's
Right.
no way of retrieving it.
Yeah, after this measurement, like these 2 guys are going to be, if you do it in this formulation, it's going to be in one of these 4 entangled states, in which case the information about the original qubit is like no longer localized over here. Or, in this formulation, they're both going to be in a separable state, and in a Z eigenstate each. But of course, you know, what happens, so, you know, to get at this point about like instantaneous like transfer or whatever. So, you know, there's the rule for this unitary correction, right? Is, you know, it'll tell you on this Wikipedia article, you know, if he gets this answer, you know, use this Pauli matrix, whatever. But consider the case where you get this answer. In other words, this is just the cap state. So this is just the, you know, up plus, oh, actually, what am I saying? Not this one.
Matt, I cannot see the board.
Sorry.
No, on my screen, I just see.
Oh, yeah. Good
Yeah,
call.
we only see a miniature view.
Yes.
I don't see what you're doing on your board, and I'm missing it.
Yeah, no. Thank you for
It looks like it is interesting stuff, so don't want to miss it.
yeah, how do I turn off the
Let me make a recommendation, Moshe, and anybody else. If you want a good explanation of this, the guy who wrote the textbook on quantum information technology, Michael Nielsen, Nielsen, has a series of videos on quantum computation and quantum teleportation. He explains it very well. Nielsen.
Yeah,
Nielsen and Chuang is the seminal textbook in the whole field, actually.
So, suppose that, you know, when Alice does her Bell measurement, if you look at it that way, she gets this answer. In other words, the up plus down state. This, you know, the state here that we started out with in terms of the two entangled particles that we called a cup state, that's going to be the up plus down state, okay? And then this is going to be the adjoint of that. So if we, you know, it's called like post-selecting. Suppose that Alice gets the up plus down state. We could pop in this cap here. And, you know, when you do that, in that particular case, you can see that the quantum teleportation reduces down to what we call the yanking equation. In other words, in these string diagrams, we can take like this and like yank it. So it looks like whatever is coming in here just goes like, and like pops out here. And you don't even need to do a correction. So in that particular case, like, you know, there's no like so-called like time delay. Like, you know what I mean? It's like, it just happens. If you got a different state, you know, this ended up being, you know, some other thing, then what Bob would end up with is basically a rotated version of the qubit that went in. And then controlling on the 2 bits that Alice would send to Bob basically undoes that rotation. So, you know, from Alice's perspective, you could say, you know, the teleportation happens at the moment that she makes her measurement. At the moment that she makes her measurement, she's like projected her qubits. And at that moment, you know, she would have to regard like Bob as like having the teleported qubit. In other words, and this is like a general feature about like the kind of multilinear algebra of like entanglement. you know, if you start off with this cup state, it's a maximally entangled state. And then Alice projects these two guys into the maximally entangled state. Like, what do we know from like the monogamy of entanglement? Now, like before, these two were maximally entangled. Now, these two are maximally entangled. And so this qubit state ends up being like squished and comes out over here. So in some sense, you know, there's like a sort of a perspectival thing going on here. It's like from Alice's perspective, you know, she'd say like, oh yeah, the teleportation happened like when I made my measurement. Like that's when I can say that that happened.
Yeah, I'm a
And
bit confused, Matthew. One moment. In the diagram that you showed us before, and the diagram from Wikipedia, it shows very clearly that Alice is sending 2 bits to Bob. So it is not just that she makes a measurement. She makes a measurement and she sends 2 bits to Bob. Any which way, she can send those 2 bits by carrier pigeon, doesn't matter. But only after Bob gets those 2 bits that are the result of Alice's quantum measurement, only then is the teleportation effectuated. This is my understanding of the picture that you had before.
well, so what I'm saying is like, suppose Alice didn't send the bits. What would Bob end up with? So there's 4 cases, right? Because Alice's measurement has 4 possible results. And in one of the cases where she gets the up, up plus down, down state, Bob ends up with exactly the teleported qubit. In the 3 other cases, she just has a rotated version of the original qubit. And so the bits that she sends allows Bob to undo those rotations.
Does Bob know what is the initial entangled pair that is being used here?
Well, yeah. So like this has been prepared in a sense by both of them, you know what I mean? And then they're, you know, in this particular state, up, up plus down, down, and then, you know, they're distributed to Alice and Bob. So yeah, that's like known, I guess, by both of them.
Okay, let me see if I understand what's going on here.
But this is unknown. Like the incoming qubit, of course, is unmeasured. So that can just be in an arbitrary superposition.
Okay, let me tell you what it is that I understand at this point, and correct me if I'm wrong.
Mm-hmm.
Bob and Alice start by sharing information about a maximally entangled pair. And let's say the entangled pair is up, up, down, down. So the total spin of the entangled pair is 1. If those are 2 electrons, the total spin is either +1 or -1. Now, Alice is going to measure the belt state of one of those 2 electrons with the qubit coming in, and the other member of the initial belt state is being sent over to Bob.
Mm-hmm.
Now, if the qubit coming in is, let's say, in the up state, and the electron that Alice got is also in the up state, then she's going to measure up, up, which is, in this case, the diagram that you drew would hold. And Bob is going to receive an electron in the down state because, sorry, an electron in the up state because it was up, up, and down, down.
Wait, so how do you mean? Like, so I'm saying, you know, Alice and Bob each share 1/2 of this up, up plus down, down state. And then they have this unknown qubit. And then Alice projects the unknown qubit and this 1/2 of the pair into one of these 4 states. So like, you know, at that moment, I mean, these are 4 entangled states. These 2 are initially separable. So like, it's sort of for Alice, like at that moment that Bob, you know, receives something, so to speak. I don't know. I'm not sure exactly what you were asking.
Okay, let me look at the following scenario. Bob and Alice start by agreeing on an entangled pair. Alice gets one electron, Bob gets the other electron. 1 hour later, this qubit comes in. Alice makes a measurement of this qubit with the electron that she has received. And the instant she makes the measurement, Bob knows what is the incoming qubit. So Bob knows the value of the incoming qubit at the same time that Alice knows this value, even if they're 10 light years away.
Well, if he measures, I mean, if Bob never measures it, then he doesn't know. But yeah, I mean, at that moment, like if Bob was, so I would say like this, like if Bob was to make a measurement and Alice happened to get this one of 4 results, this particular cap state, then Bob would get the original qubit.
But it has to be transmitted classically.
One moment.
It doesn't happen instantaneously.
A fourth of the time, so to speak, it'll work without transmitting any bits.
Oh, but then you're guessing. The point is,
Yeah,
it depends on the fact that Alice and Bob are sharing an entangled state initially. They are sharing a Bell state initially. Then when a new bit comes in, a new qubit comes in, Alice makes a measurement, and the result of that is sent classically to Bob. Not at this, you know, faster than the speed of, sent classically. Bob then has to decode it, and by decoding it, but also with the knowledge of having the same original entangled state that Alice has, he's able to figure out what that new qubit is. But none of this happens faster than the speed of light. And unfortunately, teleportation is an unfortunate designation for this, because it implies that things are happening.
Okay, and Michael, what you said right now is one scenario which makes sense to me. In this scenario, after Alice makes her measurement, she communicates to Bob the result of her measurement.
Yes.
And so let's go to the whole scenario again.
Mm-hmm.
Alice and Bob start by sharing an entangled state of 2 electrons, maximally entangled. Alice gets 1, Bob gets 1. At this point, neither one knows anything whatsoever about the electron that they have received because neither one has made any measurement. Now, sometime later, maybe an hour later, maybe a year later, this new qubit arrives at Alice's desk. Yeah, it arrives at Alice's desk, and Alice makes a Bell measurement of this new qubit with the electron she got a while ago. At this very instant, Bob still has no knowledge whatsoever about anything. He has an electron and 0 knowledge. But Alice is going to send to Bob the result of her measurement. She made a Bell measurement. She sends the result to Bob. When Bob combines the result that he just got from Alice with the entangled electron that has been sitting on his desk for a while, the result of this is going to be the state of the new qubit that Alice has received.
Yes.
So the state of the new qubit is being teleported from Alice to Bob only after Bob receives the message that Alice sends to him at the speed of light and no faster, maybe slower than the speed of light.
Well, again, kind of. So again, there's like a little bit of a subtlety. So for example, like let me show you this image here. This is from a while back. Can you see my screen again?
I can see your screen, yes.
Okay. So what I have here, like the string diagrams for each of the four situations, each of the four outcomes of Alice's Bell measurement. So in the first case here, we have the,
No, I don't see it. I don't see it. I don't see any string diagrams. I see matrices.
oh.
I see sigma 3, sigma 1.
Oh. Oh, wait, here. Did that do it?
Ah,
Okay.
now I see strings. Now I see strings.
Cool, nice. Okay, so let's just consider this first line here. So we have Alice's, so we have the qubit to be teleported coming in. We have the maximally entangled state that Alice and Bob share. This left half is, Alice's world. This right half is Bob's world. So in this case, Alice has made her measurement and she's gotten the up, up plus down, down state. That's what's represented here. So again, like when we, in the string diagrams, when we represent, the outcome of a measurement, we represent it as, like a cap, you see? In the string diagram, it's like this. Oh, you can't see my thing or whatever. A state is like something coming in like this, and like an outcome is something coming in like that from the top, okay? So the up, up plus down, down state is just in this formalism, the cap. So we can just replace that with the cap. And, in that case, the correction operation that, Bob has to do is just the identity. And so we can just like take that and yank it, and whatever you plug in here, whatever the initial qubit state is for Alice, pops out at Bob's. In the case where, say, Alice makes her measurement and she gets up, up, minus down, down, that state can be described as the cap state, but before you do it, you do a Z operator. And so because of that, the correction that Bob has to do is just another Z. And so when this operator, if you think about it, you can take, in the string diagrams, you can take the operators and like move them around the bends and the cups and the caps. When this guy hits the Z, they cancel out. And so then, the qubit to be teleported pops out at Bob. In the case where Alice gets up, down, plus down, up, that state can also be described as the X operator acting on the cap, or like, you apply the X and then you get this, then there's cap. And so, in that case, Bob wants to do Pauli X as a correction. And so when this operator blip hits that one, they cancel out. And so the qubit's teleported without any, perfectly. And then in the case where Alice gets up, down, minus, down, up, you get that little thing, and then, you basically do ZX. And so when this hits that, So you see what I mean? Like from Alice's perspective, you could say that, Bob's getting some interesting stuff at his end, like at the moment, so to speak, that she makes her measurement. But it's going to be rotated a little bit. And so that's...
Okay, Matthew, let me just tell you what it is that I understand at this point, and please correct me where I'm wrong.
Mm-hmm.
If I look at the second column, in the second column, if I look at Alice, she gets something. In the first case, she does nothing. In the other three cases, she does something represented by the matrix. 1 minus 1, 1, 1, or minus 1, 1.
Wait, what? So it's not that she's doing something. This 1, 0, 0, negative 1, and then doing a cap will give you the up, up, minus, down, down state. So this is actually just a way of rewriting this state.
Let me go back a little bit. Let's start at the top line, second entry, this very simple string, the cup at the bottom. This is the initial entangled state.
Yeah.
And let's say that the initial entangled state is 1, 1 plus down, down, down. So it is a maximally entangled belt state of 2 electrons where the total spin is +1. We know that the 2 electrons are parallel. Bob is getting 1 electron, Alice is getting the other electron. Now let's go down one line.
Mm-hmm.
Let's go down one line, yeah, right here. And again, the second thing, move, yeah, right here. Now, Alice is getting a qubit. In order to reconstruct the same entangled state that they started with, up, up, and down, down, and down, down, she must perform this operation represented by the matrix on the incoming qubit. If she performs this operation on the incoming qubit, then she's going to have a 1, 1 plus down, down. And she knows it because she measured the belt state of the 2 electrons she has at this point. She got 1 shared electron a while ago. Now another electron is coming in. She does a measurement. And as a result of the measurement, she says, I should have done this operation represented by this matrix on the incoming qubit in order to make sure that I end up with an entangled state identical to the initial entangled state.
Right.
Then she sends
Right.
this
So
information. She sends this information to Bob, and Bob is therefore going to perform the operation Z on the entangled electron that he has received. After he performs Z on the entangled electron that he has received, he ends up with an electron in the same state as the incoming electron that Alice has received.
You know, Matt, it's much easier to explain this with the actual gates. You know, this involves Hadamard and controlled NOT gates.
well, okay, so
You know, which is easier to understand than all these wiggly lines, which just diagrammatic.
well,
I think both are useful. I want to see both of them.
so
Well, like I said, you know, Nielsen's videos on YouTube explains this very clearly.
so
And he has the actual circuitry that explains how all this is done.
sure. Well, so I want to emphasize though this point because it's actually going to come up. It's going to come up in what we talk about next. So I just want to make sure that this is clear. These two things are the same. In other words, some shit comes in, and then Alice, oh, sorry, this is not right. I want minus. Some stuff comes in, and then Alice measures those things to be in the up, up, minus, down, down state, okay? That's the same as if, oh, I should erase this, it's confusing. That's the same as if Alice first did this operation, a little z, on this qubit, and then these are measured to be in the cap state, which is up, up, plus down, down. So these represent exactly the same thing. And like, it's, you know, I guess what I want to say about it is, because it's going to come up later. What, like, in the, as a vector, what is this state? you'd write it like that. 1, 0, 0, negative 1. Okay, that's this state, right? This is up, up. This is down, down. And so it's up, up, minus down, down. Okay? Look at the elements of this matrix. 1, 0, 0, negative 1. In other words, when I act on a maximally entangled state like this, with this matrix, the effect of it is to get this vector. So this is like a general property of maximally entangled states. That like acting with such a matrix here will actually kind of splay out the matrix components as a vector. So this is just a way of rewriting that. And when you do that, it makes it clear.
Okay, wait, Matt.
Okay.
Yeah, stay with this picture. Stay with this.
Mm-hmm.
Now, what you have on the left side, what you said before, Alice does a measurement. Okay, Alice made her measurement. Does she communicate to Bob the result of her measurement?
Well, yes, in this case, she would want to do that. But again, like I'm not really treating that part of the protocol. Like this is just, it's just analyzing this one part of the diagram. But yeah, so basically what Alice would want to communicate is the fact that, because she got this, Bob has to do something that cancels out this operator.
Exactly.
Yeah.
But she has to tell Bob that she has to do this. She has to communicate this to Bob. She can do this with carrier pigeon. When Bob gets the message, he does the correction, and now the qubit has been teletransported.
Yeah, but check it out though, right? Like what if Alice instead had gotten this state, the up, up plus down, down state? Then this would be 1, 0, 0, 1. This would be 1, 0, 0, 1, but look at that. That's just the identity. So in that case, Bob doesn't have to do anything.
Yeah, but he doesn't know it unless...
But he doesn't know it. Yeah, sure, yeah. But it gets a question of like when it happens. You see what I mean? Like,
yeah.
He uses the same decoding circuit. He uses a C0 and a Hadamard gate. He uses the opposite circuit from the one that was used to create the entangled pair.
In a way,
to decode the message. He doesn't have to know how she measured it because his decoding circuit will figure it out automatically, and then he'll get what the new qubit is.
Well, in a way, I mean, this is how he figures it out, right? So what Alice is telling him is essentially by saying which entangled state she got, whether it's 1, 0, 0, 1 or 1, 0, 0, negative 1, that's like exactly telling Bob like which rotation to do. Like all he does is either the identity Z, X, or ZX, depending on which state she got. And you can see that the reason for it is just that. Those are the operators that will cancel out this.
I think that what we have here is something incredibly important and incredibly subtle. And I think that now I start to see why we have the confusion between what is transmitted instantaneously and what is transmitted leisurely.
Yeah.
What happens instantaneously is the following. When Alice makes her measurement, it affects instantaneously the state of the remote electron, which may be 100 light years away. But Bob doesn't have any idea at that point what is the state of the incoming electron that Alice has received. He will know it, and the teleportation will get effectuated only after he receives from Alice the result of her measurement. So he has to wait until he receives from Alice the result of her measurement. And this is going to be a classical transmission of information. It can take forever and a day. It doesn't matter. But the state of the electron that Bob has in his possession has been instantaneously affected by the measurement that Alice made.
Yes.
So
That is the subtlety, basically. Yeah, exactly.
and this is really one of the most wonderful things that I'm starting to understand in physics, that something that I did not learn when I was in school half a century ago is the idea of two aspects of transmission of, I wouldn't say transmission of information, but in one case you have something that is being affected instantaneously, apparently in violation of the way we understand special relativity, but with zero transmission of information.
Yeah.
Because at that point, when Alice does the measurement, Bob's electron is affected instantaneously, but there's no way Bob can know the state of the qubit that Alice has received until he gets from Alice the result of her measurement.
Yeah, and as I say, he might get lucky, right? It might have been, with a certain probability, Alice gets this top line here, in which case Bob lucks out. Like, he literally doesn't have to do anything before he even receives the
That's
bit.
what he doesn't
Like,
know.
it's already there. He just has no way of knowing that unless Alice sends the bits.
Okay, he got lucky in the sense that now life is easy for him. He doesn't have to exert any effort,
Yeah,
but
exactly.
he doesn't know it.
Mm-hmm.
Can I say
That's
something? I think what we're overlooking is the purpose of this whole circuit, this whole teleportation circuit. The purpose of it is not instantaneous communication. The purpose is to be able to transmit a quantum bit by transmitting a classical bit. But the classical bit will always, be relative. It can't go faster than relativistic speed. But the fact is that in order to do this, the transmitter and receiver have to initially share a Bell state.
Hell yeah,
That's an excellent
totally. That is
point.
what makes it
That's an-
different from Star Trek teleportation. They have to have they have to share entanglement before it even starts. And for the whole thing to, be a perfect teleportation, they also have to transmit.
That's why teleportation is an unfortunate designation for this, because it makes everybody believe that it's like Star Trek, and it has nothing to do with that.
Okay. So,
well, and again, on Star Trek, I mean, you don't know.
Michael, what you said right now, what we have here, the information that is being transmitted is information about the state of a qubit. And
right.
In that sense, it is different from the transmission of a classical bit. Transmission a classical bit is one story, but you transmit a bit, this doesn't amount to the transmission, to the teleportation of a state. I'm not too annoyed with the word teleportation, because we really teleport the state of a qubit. We have Alice receives a qubit. At the end of the story, Bob has this qubit, and basically the qubit state has been teleported. And by the way, in this scenario, Alice never knows what was the state of the qubit that she has received.
True.
She doesn't have to know. Yeah, she doesn't have to know anything. There doesn't even have to be an Alice.
If she wants to know, too bad. She will never know it.
Yeah. Well, let me tell you something. If she makes a measurement by the no cloning theorem, she can't transmit it. Right. And by the way, another aspect of this is that it overcomes to some extent the no cloning theorem, where you're making a measurement of the state, but yet you can transmit it, which is an apparent violation of the no cloning theorem.
Well, in a way, you
No,
could say it's like, well, I mean,
but not really, because you're circumventing the no cloning theorem. You're not really measuring the quantum state. You're going about it in a slightly different way. You're doing a gate function on it.
yeah, you're not like duplicating it.
You're
just
not
sort of,
duplicating
like,
it, right?
by making your measure, by Alice making the measurement, it just sort of shunts the state
Right.
through this.
You're not making a measurement, really. What you're doing is you're doing a gate operation, which is different.
Well, you know,
So making a measurement also is an unfortunate terminology. You're not making a measurement. You're doing a gate operation, which is different.
yeah. Well, like Bob certainly is not doing a measurement. You know?
Well, he's doing a reverse gate operation.
Right.
But here's the interesting thing, Moshe, about all these years. It took 70 years from the inception of quantum physics until they figured out how to do this, until they realized that this could be done. That's pretty amazing that it took that long for somebody to realize how this could be done, that you could transmit a quantum state by transmitting a classical bit. It took 70 years. So
Yeah, I think
We had
it's,
to wait for Bell and Spector.
I'm sorry?
We had to wait for John Bell and Alain Spector.
Well, no, but it wasn't them who did it.
They had to do whatever they did. This was not possible before John Bell and Alain Spector.
Oh, absolutely. But this was only figured out a few years ago. This was figured out in the 21st
yeah, the early
century.
90s, I think they started using the term.
Matthew,
Mhm.
at this point, let me make a little request. Hopefully, we are going to have a session next week. I hope so.
Ideally, yeah.
If we have a session next week, would it be possible for me to have about 5 minutes of next week's session?
Yeah, sure.
The reason is that I think there are some very profound, amazingly profound implication of what it is that we have on the screen right now. So at this point, I need to draw a couple of pictures. So that's why we'll have to do it next week, because I don't have those couple of pictures.
Sure. Yeah. I mean, I agree that this is like very inspiring.
But
So-
Moshe, again, I suggest that you research which computational gates allow you to do this. And that clarifies a lot. This is just diagrammatic.
Do
The
me a
actual
favor,
quantum-
Michael. Send me some
Same
links.
thing.
I don't have any literature. Nielsen, Michael Nielsen, Nielsen. Look at his quantum information theory textbook, Nielsen and Chuang, or his YouTube videos. Look up quantum teleportation, Nielsen, Nielsen. He's Australian, but they're very good. It's about 10 lectures, 2 of which are specifically on teleportation. And he starts right at the very beginning and explains it with the actual quantum circuitry. Of course, how the circuitry is implemented is a whole other issue. That's physics. That's Josephson junctions and
That's
ion
engineering.
traps, and nobody understands that.
Yeah. But again, I mean, this is completely, these diagrams are completely equivalent to the circuit.
Oh yeah, absolutely,
it's
absolutely. But I'm saying, I mean, Matthew, I followed what you said. I can follow these diagrams because I already know how it's done. But
Yeah.
you see, but this is an actual circuit. A C0 gate followed by a Hadamard gate.
Yeah.
And that's how you create the entangled pair, the Bell state. On the other end, what Bob does on the receiving end, he's got a similar circuit, a C0 gate and a Hadamard gate that decodes
He doesn't have,
information he gets from Alice.
no. I mean, again, this is actually like a classical control. Like, in other words, depending on which of the 4 classical results he does
Well, yeah,
either I, Z, X, or ZX. So it's just a
By
single
the way,
qubit.
Matthew, can you go back to the previous picture?
Mhm.
a C
Yeah,
nine is
one
classical.
moment.
Yeah.
In this picture, the picture that you have with the C naught and H gate,
Yes.
you have simple lines and double lines. What are the double lines?
A single line means a quantum transformation, and a double line means a classical.
Yeah, that's right.
Okay.
That's
Okay.
not even important.
Yeah,
Look
and
at the
actually,
videos. You'll understand this very well.
yeah, to be fair, I actually don't know what is being exactly signified by this little plus here and this dot. Yeah, maybe there's another way of thinking about
Well, that's a
expression
C naught. That's a
operation
C naught gate.
that you're referring to. So,
That's how you indicate a C naught gate with that.
well, but
dot
here
in it.
they're along the same line, you know.
Yeah.
So sure.
No, the other dot is just the
Yeah,
connection.
this is a C naught, but yeah,
Yeah.
I'm not sure what they're trying to say here. But all right, so quantum teleportation is great.
I just have to say it, very clever, very clever. Neat stuff.
It only took them 70 years to figure it out.
So when we talked about wormholes before, it was sort of based on this paper, Quantum Gravity in the Lab, which was, it's just a nice sort of introductory paper in a way, meant to inspire people to play around with this stuff. And they offer this protocol for kind of simulating something like a wormhole. And, it's really reminiscent of the teleportation thing, right? So we have a left side and a right side. We start off left and right are in the so-called thermofield double state. In the case of like infinite temperature, that's just going to be a maximally entangled state. And then you can kind of be like, oh, at a different temperature, it's like a little degraded or whatever. And then on both the left and the right side, they've divided it up into AL, BL, BR, and AR, where basically AL is going to be, it's sort of divided up into like the parts that have to do with the message and then like the rest of it. And then like the parts that have to do with the output and then like the rest of it. So basically you start off with this sort of like entangled state. And then there's a Hamiltonian that acts on, say, like the one side and the other side. And they're separate, but each is the transpose of the other. So HL, the Hamiltonian on the left, is equal to the transpose of the Hamiltonian on the right. And the idea is that, people think that, like, in what sense does this represent two entangled black holes? The idea is like black holes are going to be scrambling. They're supposed to be the fastest scramblers in nature. And so this is a Hamiltonian that's like, you kind of like maybe, swap a state in to your general state and you start evolving out of this Hamiltonian very quickly. Any information that's like localized somewhere is going to get scrambled out over the whole state. And like, that's why these are supposed to model black holes. Like, obviously this is like not taking into account like anything specific about black hole physics. It's just like they're scrambling. That's all. That's like the only thing.
Matthew, one moment. I missed the point. What is AL and BL? What are A and B?
Right. So think about it like AL and AR are going to be kind of like where we're keeping our message. So AL is kind of like where we're going to put the message in, and AR is where the message is going to pop out, and BL and BR are like the rest of the black hole.
The what? BL and BR are what?
So on the left here,
what is BL?
It's like the rest of the left black hole. And BR is like the rest of the right black hole, ignoring the part about where the message is going to come in and where the message is going to come out.
Okay.
Matt,
So-
can you expand this horizontally because the text, no, not expand it, not enlarge it, because the text is cut off
right here.
on the side. Yeah, that's good, thanks.
So we have this entangled state between left and right, represented by this TFD. So first, we evolve backwards in time with the left Hamiltonian. So e to the I, right? Usually the convention is that, right? Like e to the negative I is evolving forward in time, and positive sign is evolving backwards in time for whatever reason. So first step in the protocol is like you start out with an entangled state of two whatever black holes, left and right, and then you evolve the left part backwards in time. Then you insert your message. The idea here is we just sort of swap the message in. You see that's what this is doing. We take the AL part of the black hole, and then we have like an input thing that we want to put into the black hole, and we just swap them, and then just like ignore this part. Okay, so we're basically just swapping in the message. Then we evolve the left side forward in time. Okay, so all this is doing is just saying we throw a black hole into the qubit sometime in the past. So like take the left side, evolve it backwards in time, swap our message in, and then evolve it forward in time. Then we have this coupling. It's like an external coupling, a classical coupling, in the sense that V is going to be like diagonal. A classical coupling between the two sides, left and right. And you can see that this coupling is just going to act on BL and AR. In other words, it's just going to ignore the message subspaces, okay? And then after we do this coupling for a little bit, we got to determine what the value of G should be to like optimize this, basically. But then afterwards, we evolve the right side forward in time with the right Hamiltonian, which again is the transpose of the left. And when we do that, this state psi in should pop out here at psi out. So again, we start off with two maximally entangled states between left and right. We evolve left side backwards in time, swap in the message, evolve it forward in time, couple the two sides of the black hole for a little bit, and then evolve the right side forward in time. Again, TR and TL, the amount of time is the same on both sides. And then basically in a kind of teleportation-like thing, we'll get the state that came in on the left will pop out basically on the right if, we've chosen the right coupling here, we got a good value for G, and the Hamiltonian we chose is appropriately scrambling. So, kind of the idea is that like when you put the message in, and then we evolve the left side forward in time, it kind of scrambles the message over the whole left side of the black hole. And then we kind of do this coupling. And then this forward time evolution on the right side kind of unscrambles it. And you could think of it like it kind of, the qubit refocuses, gets like unscrambled and pops out on that side.
One problem that I have here is the following.
Mm-hmm.
If I try to view it chronologically, what's going on here? When I look at the three leftmost lines, chronologically, they're going down. Time going forward means those three left lines are going down. Then the two right lines are going up. That's the chronological course of events. but e to the IGV seems to be an interaction between the two events that are not in the same time. One is in the past and one is in the future. How
Well,
can you have this interaction?
so like if you're doing this, like implementing this protocol, time is gonna flow from the bottom to the top. And this sort of backwards forwarded time thing has to, with these, which is indicated by these green arrows, has to do with the sign here. So, e to the I is gonna basically do backwards evolution, and this is gonna do forward evolution. And so this is, this is sort of like a circuit representation. Like the story you would tell is basically sometime in the past, a state fell into the black hole on the left, after which it got scrambled. And that happened for a bit. And then someone coupled the two mouths of this wormhole. Someone coupled these two black holes together. And then you waited for a bit on the right side. And after a while, the egg unscrambles and out pops the qubit.
Oh, so e to the IGV is the wormhole.
You can think of this more like the, in the teleportation thing, it's like sending the classical bits. So like this is, the wormhole equivalent of Alice sending 10 or whatever to Bob. And in fact, like instead of actually doing this, you can actually do a measurement instead. Like obviously that's sort of unrealistic for like a real black hole. But instead of doing e to the IGV, you can do like basically like Alice, on the left can like make some measurements of these things, send those classical results to Bob. He, does some operations based on that. And that's like another way of doing this protocol. There's a footnote they have here about that. Here. Instead of acting with EIGV, one can simply measure all of the left qubits, the carrier qubits, not the message ones, in the Z basis, send those measurement outcomes over to the right side, and then act with this operator on the right. And then it's like literally like quantum teleportation. The V coupling is classical, and so it's no more, no less than actually just sending some classical bits. And they take V to be these ZZ operators. In other words, it's a sum over they call them the carrier qubits as opposed to message qubits. And it's a sum over, Z times Z on the left and right. And this is what they've chosen to be V. And we'll see in the model we'll talk about today, there's like a more elegant sort of thing. Like you might wonder like, well, why does that work? There's sort of interesting reasons. And we'll see in the context of these Majorana fermions and the SYK thing that the operator that we choose becomes very obvious and actually more satisfying than that. So, so that's like a lightning review of the wormhole thing. Any questions about that before we start talking about the Majorana fermions and stuff?
Yes, two comments.
Mm-hmm.
One comment, Matthew, I really appreciate the presentation. You explain things so clearly that even I can understand them, or at least I can delude myself that I understand something here.
Yeah, at least for the duration.
I understand, that's another story. And the other comment is that I still don't quite see the wormhole here.
Well, I mean, I would say that how do I want to say it? Na, 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 na. Just drawing a little diagram over here. Yes. La 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 la. Okay, how do I stop share? Okay, wait, can you see the board again?
Yeah, yeah.
So here I've sort of drawn out the teleportation thing, so it like looks the wormhole, so it looks exactly like teleportation. So here's some kind of maximally entangled state across left and right. Here's the message that we want to pop in. We, evolve the left side of the black hole backwards in time. We swap in our message. We evolve the left side forward in time. We do a classical transmission of information, followed by some kind of correction operation. And then we evolve this forward in time, and then this guy pops out. So, what I would say is that the wormhole is kind of like where is the wormhole? In just the same sense as quantum teleportation, it's like, it's right there. It's this. It's like the wormhole is provided by the initial entanglement between the two sides.
One question. On the left side, you have those two lines crossing. Is there any meaning to the crossing?
So that's like a swap. So you're taking the message and you're sort of swapping it in. Again, like this really should be, there should be like two things coming out of here, right? We like swap in for part of the black hole, the message, and then like leave the rest of the black hole. You see what I mean? Like in this diagram here, it's like we have, they call the BL the carrier qubits and AL the message qubits. And so they're both part of the left black hole. And we just sort of swap in the message for the AL, leaving BL untouched. So that's just sort of, that model's like inserting the qubits into the black hole.
So Matt, I have a basic question, which you may or may not want to answer. How do we extract information from a black hole? In other words, on the receiving end, how do you get the information out? I thought nothing can leave the black hole.
It just pops out.
How does it pop out? Where does it, in what form?
Pops out. Yeah. I mean, I guess the way they sort of think about it is like the classical coupling has the effect of kind of moving the event horizon like inward.
Oh yeah.
Revealing the qubit that would have been trapped inside there. So yeah, it just sort of flies out of the black hole. Yeah, totally.
So is this electromagnetic radiation that pops out?
No, it's just the original thing. Yeah, I mean, it literally is like you fly your spaceship into the black hole and then you'll fly out the other black hole.
Oh, so it could be material stuff too. It could be a spaceship.
Yeah, I mean, that's what they're, yeah.
And it doesn't get sucked back in due to the tremendous gravity?
It's going fast enough. Yeah, like the idea is that this sort of, you see in this diagram here, the way they've sort of explained it is that you could think about it like the coupling kind of, like moves the event horizon inward or whatever, sort of translates the qubit, like so it can escape. It's actually, outside of the event, becomes
But
outside
it would,
the
ha-
event
it would have to
horizon.
be going faster than the speed of light, or at least at the speed of light. And how does a material object go that fast?
Well, no, I mean, well, depending on how, I mean, it's like, it was inside the, it's like inside the black hole, the event horizon moves,
Yeah.
and then it, yeah, like if it was moving slowly, maybe it gets sucked back in, but like, so I think that's the right way of thinking about it. Yeah, it's not like it's going faster than the speed of light, and so it's able to like escape the pull of the black hole. It's more like the black hole has changed. In other words, like the geometry of like where its event horizon has like changed, and so it just happens now that
Or it just
it's no
appears,
longer inside of it.
it appears outside of the event horizon.
Yeah, like I picture it like you fly your spaceship into the left black hole, and as you get closer and closer, you get like red shifted and kind of scrambled out over the left black hole, and you kind of fade out. And then, sometime later, you're looking at the right black hole, and you start to see something like coalescing, like around its surface, and then it kind of like recoheres, and then it's like, whoa, my God, there's a
Sure.
That's what I'm picturing. Yeah, I mean, basically.
Of course, this is what the Schwarzschild observer sees. The actual, which is probably irrelevant, the actual observer.
Yeah, what the dude
But this
inside. This is
teleportation happens instantaneously, right?
Well, yeah. So so there's an interesting question here of like, and they talk about it a little bit in the paper. Yeah, so it's like, what's the experience of the guy who falls in? I mean, they're going to see some geometry, some wormhole geometry, and the question is, like, could you reconstruct aspects of the wormhole geometry from studying how it changes actually, like what goes into it? In other words, if you had perfect teleportation or whatever, like exactly what falls in is what falls out, in which case you get no information about what was going on like inside the wormhole. But maybe, shit happens, right? Like in the wormhole geometry. And so the state that comes out is like a little bit different. And then could you study that and like reconstruct something about,
I'm afraid that a material object could not, undergo this, because I think there are some theories that show that you can't keep a wormhole open long enough for a material object to go through. Maybe it's just information. Maybe it's just information that's transmitted.
No one's saying it's gonna be easy. But like, it's like, there's a paper, about where people do some kind of, I would say somewhat rough calculations about like, so like if you actually wanted to fly a spaceship, how big would these black holes have to be? Like how plausible is it? And what we know now is that it would not be easy. So,
No, but again, maybe it's just information that could be transmitted. We don't know, and then it would have to be reassembled at the other end. Information, I could see being transmitted.
Picture that you are looking at right now.
What's that?
I have a question about the picture that you are looking at right now. We see two squares. My guess is that each square is a Penrose diagram of a black hole.
Yeah.
If I look at the left square, I see the horizon of the black hole. I see a message falling into the black hole, and the message ends up in the singularity. Mm-hmm. And this is the picture that you are all familiar with.
Yes.
That's what happens. Now, if we look at the right picture, then something very strange happened. We have the message coming in, it falls into the black hole, then it goes backwards in time. Now, the reason Penrose came up with his eponymous diagram is to have an easy analysis of causality. The speed of light is always at 45 degrees going forward. And having something at 45 degrees going backwards is antithesis, complete antithesis to the whole concept of Penrose's diagram. This
Yeah, I know what you're saying.
segment
Yeah,
going back in time is not possible in a Penrose diagram. To add insult to injury, it is within a tunnel of negative energy.
yeah. I mean, this is an aspect of things that I confess due to my ignorance. I don't fully understand these.
They look like
Wait, say
null
that again. I
geodesics.
like dropped out for a second. I like my internet
Yeah,
went.
can you show those pictures back?
Yes, 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 yes. Okay.
Well, potential energy could be considered negative energy
Now,
in some sense.
if you look at the right picture, there are two things that baffle me completely. Number one, the message comes in and it propagates at the speed of light into the black hole. It continues at the speed of light.
Mhm.
Then it goes backwards in time at the speed of light, which is the exact antithesis of a Penrose diagram. In a Penrose diagram, this segment is not possible. That's the reason Penrose created those diagrams.
Question
So,
is the
one moment.
Yeah.
So I do not understand this segment, number one. Number two, I see negative energy that seems to be propagating along null geodesics. What is the negative energy that propagates along null geodesics? Obviously, it has nothing to do with the horizon. The horizons are the diagonals. The negative energy are not the horizons. It looks like one is coming in from the left, one is coming in from the right at the speed of light. And I do not understand the message propagating backwards in time at the speed of light along one of those negative energies. So I'm looking forward to some very clear explanation,
Yeah.
like all the explanations have been so far.
So I am not going to be able to give you that very clear explanation. Unfortunately, you know, I understand this stuff in a way, like at the level of like the qubits and the protocol. Like, I mean, this negative energy stuff aside, right? You know, I understand it at the level of, okay, you have two entangled systems and some message gets scrambled over the one, and then there's some coupling, and then it, you know, kind of unscrambles on the other side, and that makes sense to me.
Can I make a
Then
statement?
wait, can I just say this one thing? So then there's this whole like interpretation of that in terms of, you know, wormhole geometry and like all this other stuff. And I understand that much less. It's a little bit, you know, just like above my pay grade, basically. So, you know, consult
Can I
with
say the
these
fact
papers
that
and so forth to get a better idea. But yeah, it's basically what they're saying is that this coupling of the two sides, as they say here, is going to send like a negative energy shockwave. And when, I guess a little bit better way of saying what I said before, like about the event horizon, you know, kind of getting pulled back, it's more like they're saying here, the message hits the negative energy shockwave, which translates it backwards in time in such a way that it's beyond the event horizon, so it can pop out.
doesn't the entanglement imply, Matt, doesn't the entanglement imply instantaneous transmission? So you don't have to worry about all of these factors. The entanglement itself implies instantaneous transmission from one black hole to the other.
Well, sure, but it can't come out. You see, it's like that would be like this left diagram. Sure, the left and the right are entangled, but the message is still trapped inside.
But it can appear at the event horizon of the second black hole. It appears at the event horizon.
Well, no, I mean, no, you know, it'll, as I say here, it'll hit the singularity. Singularity. Yeah, in order to get this, to get it to come out on the other side, just you need this coupling, which actually puts our earlier discussion about teleportation in an interesting light. I'm not sure what to say about it, right? We were talking about the teleportation. It's like, oh yeah, when, exactly when Alice makes the measurement, the thing is teleported, but then there's this correction. Here it's like, well, I guess it makes sense. The coupling is basically the equivalent of the measurement and the transmission of the bits in one. And as I say here, you could, instead of doing this sort of coupling that's just a continuous evolution, you could also implement that as a measurement. Like why negative energy, how exactly this geometry works. I unfortunately can't answer too many of the really deep questions here. It's something I wish I understood better. But.
Okay, let me take a minute to tell you something that probably you know already about myself. Two things about me. Number one, I'm a very lazy person.
Uh-huh.
Number two, I'm a very selfish person. So let me expand a little bit on those things. One of the reasons I like those sessions, I really enjoy them, is because I learn a lot, number one. And number two, I enjoy them because I really have a good time. Besides learning, just interacting with you guys, I'm having a good time. And since I'm selfish, it makes me happy. That's wonderful. Now, because I'm lazy, I would really like someone, maybe you, Matt, to explain more.
Yeah. Well, I'll send some links out to some.
If you don't get the explanation right now, no problem. If you can explain it maybe next week or the following week, whenever, I would be delighted if you're willing to do this. I would simply be delighted, that's all.
Sure, it's definitely something I'll be learning more about. Again, I'll send out some links to lectures of, given by some of the people who wrote this paper, where they can go into a little bit more, detail or whatever. I just don't trust myself to say anything too intelligent about it.
Here's another possibility. In Dirac theory.
One moment. Like for instance, the sentence which says the message hits the negative energy shock wave. Where does it come from? Where is the negative energy shock wave? What is a negative energy shock wave? In a Schwarzschild black hole, I understand how Schwarzschild black hole forms when you have the collapse of a heavy star. You have a star, an old star, 10 solar masses, it collapses into a black hole. Where is the negative energy shock wave? Where does it come from?
In Dirac theory, negative energy is reinterpreted. Negative energy could be antimatter. You would reinterpret negative energy as it's done in Dirac theory.
So, there's a footnote to it, and they reference this paper from 2016, 2017, and they say, after turning on an interaction that couples the two boundaries of black hole, we find a quantum matter stress tensor with negative average null energy, whose gravitational back reaction renders the Einstein-Rosen bridge traversable. So, again, heady stuff. I'm not going to be able to go into this, but I can. But maybe instead we should talk a little bit about the SYK stuff, because I can say something about that.
Now, one moment. Let me tell you one thing that I do understand. I think I can see how you can have a negative energy shock wave inside the black hole, because a particle inside the black hole can have negative energy. So the black hole can be saturated, and I'm sure that it is saturated with negative energy particles, and you can have a shock wave propagating through those particles. Just like you can have a shockwave propagating through any collection of particles. But I don't know if this is what they're talking about here. And
Now-
I still don't see how information could move backwards in time if
So-
you have a negative energy shockwave.
Yeah. So I have no idea if this is actually what they're talking about, but this is what I thought of. You know, it's maybe, again, grain of salt. Like, I don't know. There's like those papers are complicated. There's things I don't understand. Okay, just like not saying this is the right answer. But you know, when you think about what we're talking about with teleportation, like start off with, you know, some entangled stuff. A qubit comes in, and then, you know, Alice like makes this measurement or whatever. And it, like, let's say we're just dealing with the case where she gets up, up, plus, down, down, and so this is just a cat. I mean, what would we say about this qubit? It goes in, bounces off this measurement, goes backwards in time, goes around this, and pops out here. So, I mean, that's my intuition about it. It's the same sense, like backwards in time, as the idea that this equals this.
Okay, Martin, what you said right now, when you talk about backwards in time, I see it merely as a figure of speech. It is not something that happens physically. Physically, this is not happening.
Yeah,
Feynman explained this.
This, I guess it's a perspectival thing, right? Like from the person who's like putting this qubit in here and who's like prepared this, right? Time moves forward in this diagram, I guess. But like if you were this qubit, I mean, I don't know what to say. Maybe, you know, it's like their notion of time might follow this line instead.
Gentlemen, Feynman explained this. Feynman said that an antiparticle moving backward in time is equivalent to a particle moving forward in time. You have to redefine the equations, what you mean by backward in time. It's negative energy moving backward in time is the same as positive energy moving forward in time. But nothing can go back in time. That's logically ridiculous because then I can go back and kill my grandfather. That's ridiculous.
Well, yeah, does that,
By the way,
fall into the
Michael,
category here?
Michael,
I don't know.
Yeah.
the difference between you and I, if it was possible, you would kill your grandfather. I would go backwards in time and tell myself in the past the stock market today.
No.
What was that? I missed that. What did he say?
Read the stock market report.
No, I'm saying this is the grandfather paradox. If you go back and kill your grandfather before he reaches puberty, then you can't be here. So it's a logical inconsistency.
Yeah, this is what you would do. I would do something else, but
I'm not saying I would do it.
Well, I mean, it's interesting to think about here. Like, you could say that this qubit goes up and then goes backwards in time.
No.
From the perspective of someone outside, it just looks like the qubit teleports in space.
Like I said, Feynman explained
Right,
it. An antiparticle going with negative energy going backward in time is the same as positive energy going forward in time. Feynman explained it. So what more do we don't have to argue about it. It's been explained.
Well, you know, I mean, I guess what I'm saying is that there's two weird things in this diagram. One is that something over here in space ends up popping over here in another part of space. And then the other thing is that it seems like there's a sort of forward in time, backwards in time, forward in time thing. And those two weirdnesses are the same weirdness.
But they can never violate acausality. They could happen faster than the speed of light through entanglement.
Right.
But
Well,
they
so like,
can't-
for example, like what if this?
But
what
they
if
can't happen acausally where, B occurs before A that caused it.
Yeah. So like, for example, if like someone, say like make some random measurement of this,
Yeah.
Sure, like this qubit, it's going backwards in time or whatever, but there's no way of getting the state out. right? Like, remember, for you, time goes like this. So even if this state is like coming in from the future, it's like hardly matters to you. It's only if it can like go around another bend that it can pop out.
Well, that's not my understanding of quantum teleportation. If you want to believe that, okay, but I mean, there are causal ways of explaining it completely.
Well, I just sort of try to take the diagrams like, literally, like in the sense, like if the whole thought, right, is that like,
Matt, wait. Yeah, this diagram. Yeah.
if we're supposed to be
One
allowed to,
moment. Matthew, with this diagram, what you said before about going backwards in time, again, I see it as a figure of speech. Okay, we can view it as going backwards in time. In the laboratory, what we are doing, we create a bell pair, we send one electron to Alice, one electron to Bob, and then when we look at the whole picture, figuratively speaking, it is as if the incoming qubit is going backwards in time. Okay, I don't have any problem with using this as a figure of speech as long as we don't really take it literally. Yeah, now the qubit is going backwards in time. No, we know that this did not happen. Now, at the same time, I can see, not yet, but I can see that potentially this could lead to an analogy with the picture that we saw in the paper that you showed us before, where we see a segment going backwards in time. Aha, maybe that's what's going on here.
yeah, and again, again, like none of this backwards in time stuff can happen unless there's entanglement. In other words, it's
right.
Precisely this fact that you get an entangled state as a result here that allows this to kind of like bend around, and it's only because this is an entangled state here that you can kind of continue the bend.
That's
So
right.
There's none of this backwards in time shit like without entanglement.
No. Being incredibly optimistic, I'm willing to live in a dream world where eventually we will understand how this picture that you drew right now meshes in that the picture that you showed us before with the segment going backwards in time inside the negative energy, null geodesic, which I do not understand at all. But okay, I can see that there are some analogies here. And
Yeah,
maybe,
that's my intuition. I'm not totally sure if that's rigorous, but that was my thought. So
Look, entanglement violates special relativity.
no, it does not.
But it does not violate causality. There's still causality.
No,
If
it
A
does not
causes B,
violate.
then B can't come before A.
Michael, that's exactly what I want to stress next week. Is it does not violate special relativity. It is not obvious. It looks like it violates special relativity, but it does not.
What does not? You're talking about entanglement?
Yeah, entanglement does not violate special relativity.
Well, that's a new one.
Next week,
No,
I will show that it does
with
not violate special relativity.
I don't think that's been accepted. We'll have to nominate you for the Nobel Prize, Moshe, if that's true.
No. It is, when you see it, it is trivial.
Huh.
It is trivial.
No, but special relativity assumes that there is an upper limit to speed, the speed of light. Entanglement violates that.
We will talk about it next week.
Yeah,
but
let's save that for next week.
One moment, Matthew, can you go back again to the picture with the negative energy and the segment that goes backward in time?
Yes.
The one that gives me lots of heartburn? Yeah, that's this one. If we go back to the analogy that you made before with the string diagram, and we look at the evolution of this message, it goes up, then it goes down, then it goes up. Presumably, there are two entanglements here. The analogy would be to say that the lower corner along the trajectory of this message is one entanglement that's being created up front, The top corner is the other entanglement, which would correspond to Alice making a measurement. And in order to have the message received at the other end, now we have a problem. Now we have a problem, and the reason what I was hoping is not going to work is the following. What we saw before with the string diagram is that Alice makes a measurement, then she communicates to Bob the result of her measurement. Only then can Bob decipher the information about the incoming qubit. In this diagram, there's no way Alice would be able to send this message to Bob because it will have to go through the horizon. It will have to go faster.
Well, again, so the coupling is, you know, somewhat equivalent to Alice making a measurement and transmitting the result to Bob. In other words, it's like someone from outside coupling the two black holes together.
Where are the two black holes here?
So like here and here. So this is the event horizon of the left black hole. This is the event horizon of the right black hole. And the idea is they have like a shared interior.
Matt, can you post the link to this paper?
Yes.
Do you have it handy? I mean, could you put it on chat?
I used to.
Or if you could, you know, put it on the website. Or...
Yeah, it's somewhere on the website. I forget where. Yeah, I'll just send it to the chat. Chat. Yeah, it's a nice paper.
It's a bunch of, as we say in the physics community, bullshit, but, you know, it'd be interesting to read.
Well, hey, I mean, like I keep saying, okay, whatever you can say about, you know, astrophysical wormholes or like whatever, you know, the point of this paper is saying like, hey, we got quantum computers now, you know, I mean, 20 qubits, play around with it. You could, you know, 10 of them are the left black hole, 10 of them are the right black hole. And
Really?
you can do it. I mean, yeah, it's like, that's what I'm saying. It's like you can just implement this protocol as like a quantum.
What about gravity? We're leaving out gravity.
Yeah, exactly. Like the only thing that's being modeled is just this idea of like two entangled systems. Message goes in, there's scrambling, there's a coupling, and then there's like unscrambling. And, you know, to the extent that it models a black hole, it's like, you know, there's this idea that like if you can get two entangled black holes, and then black holes are supposed to be fast scramblers, like that's what sort of licenses this like interpretation.
But you would also need a quantum model of gravity, which we don't have. So
Right. So it's not, it's this, you know, these are just very simple models. Yeah, it's obviously not in itself realistic. Although, you know, and people have developed like much more you know, realistic models. So we should talk a little bit about, I don't know if we're going to get to the full SYK thing today. It was very good to go over this review of both the teleportation and the qubit wormhole model, and especially, yeah, if Moshe gives a little talk next week, you know, it'll be perfect segue to continue this discussion. But before it gets too late, I do want to just set up a couple things about the Majorana fermions and a little bit about how that'll work. If that's okay. Just so you can chew over that. And we'll see an interesting connection to these sort of cups and caps, basically. So, all right, this was just a little review of, you know, bosons, fermions. We actually already talked about this. It's sort of copy and pasted from another talk. If we have a bunch of fermions, you know, we can form, you know, creation and annihilation operators. We have a kind of oscillator that keeps track of the number of fermions in each possible state. But of course, unlike bosons, these oscillators can only have 0 or 1 excitations. In other words, Pauli exclusion principle, only one fermion can be in a given state. Fermions are permutation anti-symmetric. And what that means is that if, you have, fermion creation operator I, fermion creation operator J, you act with J first on the vacuum, and then I, versus acting with J, oh shit, this is completely fucked up. Okay, wait, it should be JI. If you act with Fi and then Fj, you get the negative of what you would do if you act with J and then I. In other words, the changing the order in which you act with the fermion creation operators gives you a sign flip. And this is related to the fact that if you have a bunch of fermionic degrees of freedom, the commutation relations basically involve the anti-commutator instead of the commutator. So, for bosons, you get, commutator of the annihilation operator on I and the creation operator on J. It's going to be the identity if I equals J. Here, it's instead the anti-commutator. And, it's great in a way, fermionic degrees of freedom, because it's, going to be finite, basically, in the sense that, for bosons, each harmonic oscillator could potentially have any number of excitations. For the fermionic degrees of freedom, it's just like 0 or 1. So, you can just basically, for a given degree of freedom, you can represent these creation and annihilation operators as just these simple little 2x2 matrices. But when we kind of tensor them up, we have like multiple degrees of freedom. We have to implement these commutation relations. In other words, we have to get this sign flip. And so, we talked about this a little bit a couple weeks ago, I guess. The way to do it is to, instead of just, upgrading each of the operators with identities, you also, stick Pauli's Z operators appropriately in here. And the idea is like this works because, suppose you're in the vacuum state and you act with F4. It creates a fermion, but, and then does like Z, 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 Z on the first 4 fermionic oscillators. But that doesn't matter because there's no excitations in them. So that has no effect. So if you act, 4, 3, 2, 1, 0, then you create a fermion in 4, create a fermion in 3, create a fermion 2, create a fermion 1, 0. No need for a sign flip. But if instead you created them, say, flip the order, you did F3 and then F4, then it would matter. So if we did, F3 first, then we've got like a little fermion in this oscillator, and then we do F4, it's like we create a fermion here, but this Z is relevant. And so that gives us our sign flip. And so we can check that if we build up operators like this, they satisfy the correct commutation relations for the fermionic oscillators. So here, this code here just does this. And this code tests the fermion operators, just makes sure that, checks these two things. These should be 0, and these should be the identity if I equals J. And, it's true. Oh shit, nice. Computer says it's true. Okay, cool. So we've got our fermionic oscillators with the correct commutation relations. Great. So that, so far, we talked about that a couple weeks ago. So now we turn to the question of like, well, what are these Majorana fermions? So, it turns out like you can take a normal fermion, and actually I'm going to call these normal fermions complex fermions. Why? Because it turns out you can take a complex fermion and decompose them, break them into 2 Majorana fermions. And, the idea here is that, a Majorana fermion is its own antiparticle. And what that means effectively is that its creation and its annihilation operator are the same operator. You can think of them kind of like a Majorana fermion's like the square root of a normal fermion. And just as we can take a complex fermion, a normal fermion, and split it into two Majoranas, we can take any two Majoranas and fuse them into a normal fermion. So it's easy enough to create these Majorana operators. If you have a fermionic oscillator, it's got, you know, annihilation creation operators given by, say, F and F dagger. And we can form two Majoranas out of them. They're just gonna be linear combinations. We just creation, annihilation added together with a little square root of 2 and subtracted, multiplied by I, 1 over square root of 2. So it turns out psi is the usual way of notating one of these Majorana operators. And we've chosen to call, you know, one of these Majoranas left and one of them right for reasons we shall shortly see. Indeed, these are going to be, we're going to build our two entangled black holes out of left Majoranas on the one hand and right Majoranas on the other hand. Furthermore, although the normal fermion creation and annihilation operators are not Hermitian, the Majorana operators are. Furthermore, if we have a bunch of Majoranas, they will obey this commutation relation. So the anti-commutator of two Majoranas is going to be the identity if I is equal to J.
I and J, those indices takes the value left and right, or
yeah, that's a little, you know, bad notation there. Yeah, it's not left and right, but like if just any number of Majoranas. So you just have a set of Majoranas. They should obey these relations.
Oh, Matt, aren't these vial spinners? That's what they look like, or while, as you may say. While spinners are left and right decompositions.
It's kind of a different thing.
It is yeah, it would have to be because, you know, vial spinners do not give you.
Yeah. So the difference is, so you can think of like, what is that? I'm trying to remember. I don't know this that well, but it's like, I mean, you can think about the Dirac spinner or whatever, like as being composed of two vial spinners.
Right.
Basically, a left-handed one and a right-handed one, or from another perspective, kind of like particle and antiparticle. This is a little bit different.
Well, no, not actually particle and antiparticle. In fact, there are right-handed and left-handed electrons, for example, that have different characteristics.
Yeah, but I mean, there's another way of looking at it. Like instead of breaking it into like left and right, you can also break it into like matter and antimatter.
Okay.
Yeah, that's a whole thing. It's a little different here.
So are we creating a real wave function as opposed to a complex wave function? Is that the point of this?
Yeah, that is related to this Majorana idea in the sense that, like, to the extent that, you know, the creation annihilation operators are the same, that their own antiparticle, there's this relation to real valued wave functions. That's not really going to come up so much in what I'm going to say here. But so wait, let me just switch to this back to my whiteboard just for a second to describe this following thing. So suppose we have three, let's call them complex fermions. Again, by complex fermion, I mean like a normal fermion. I'm just gonna call them complex because we're like breaking things down into Majoranas. So suppose we have three of those, okay? And then we split each of those into let's call this like 1, 2, and 3. Okay, okay, a little sloppy there. You're kind of squished. Okay, so we have 3 complex fermions. And we split each one into a left Majorana and a right Majorana. So from 1, we get, this guy, psi left 1, psi right 1. And then from 2, we get psi left 2, psi right 2, et cetera, et cetera, et cetera. And actually, wait, this is better. Should do 4. Even number is better. That's just, okay, 4 complex fermions, and then these are Majoranas. Okay, kind of sloppy there. So, okay, we had 4 complex fermions. We split them each into 2 Majoranas. Now, what I'm going to do is I'm just going to gather up all the left ones. And I'm going to gather up all the right ones. Okay? And then I'm going to make new complex fermions. I'm going to fuse these 2 into a complex fermion, fuse these 2 in a complex fermion, fuse these 2, and fuse these 2. Okay? Does that make sense? It's start off with 4 complex fermions, split them each into 2 Majoranas, left and right. Then I think about just the left ones and just the right ones. I have 4 left Majoranas, 4 right Majoranas, and then I fuse the first 2 left ones into a new complex fermion. Fuse these guys into another complex fermion. Dun, 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 dun.
You're going to show us how you fuse them, yes?
Sorry, say it again.
You're going to show us how you fuse them.
Yeah, totally.
Okay, great.
So so then what you get is we just start off with 4 complex fermions. And then here we end up basically with 2 left fermions and 2 right fermions. And now here's the cool thing. If these 4 fermions up here that we started with are in the vacuum state, and we do this operation, split them each into 2 Majoranas, gather up the left ones, gather up the right ones, fuse those into new fermions, fuse those, we end up with 2 complex fermions on the right, 2 complex fermions on the left, on the right. These are going to be maximally entangled across left and right. So again, if we take these 4 fermion oscillators, they're in the vacuum state, no fermions, etc. We do this operation, we end up with a maximally entangled state across the left and the right fermions.
Okay, Matthew, even though you're not going explicitly into the fusion operation, I can accept it. Okay, that's neat, that's great. But operationally, what does it mean? Start with 4 fermions, let's say 4 electrons that are completely independent of each other. What are the 2
Yeah, how to do it? I have no idea. I don't know. Yeah, I mean, I don't know. How do you take an electron and do some weird thing so that it's 2 Majoranas come out and then whatever. Yeah, I have no idea. When I say fuse, I just mean running this equation in reverse. Wait, let me go back to my screen. So, you see here, if we take basically the sum of the creation and annihilation operators of a single fermion, we get a Majorana. left Majorana. If we take the difference multiplied by I, we get a right Majorana. Well, we can just run this equation in reverse. I didn't write it out, but here, I have it in code here. In other words, you take one Majorana plus I times another Majorana, and that gives you an, what is it, a creation or annihilation operator? Yeah, annihilation operator. And then you take the Majorana, one Majorana minus I times the other Majorana, and you get the creation operator of a new fermion. So, when I say fuse, like at the very least, you can construct these operators. You see what I mean? And this kind of thing should remind one, in any case, of what we do all the time, like how we even get the creation and annihilation operators to begin with from like position and momentum. This is a very similar equation to, the creation operator being, what is it, x minus pi or whatever, and annihilation being x plus pi. Similar kind of thing. We're taking like linear combinations of stuff. So again, it's just running this in reverse, right? It's like solve this for f and f dagger given psi L and psi R.
Okay, Matthew, stay with this equation for a minute. What you said right now is perfectly clear. I can see how you can take the inverse of those. You just multiply the second equation by I, then you take the sum and the difference of the two equations.
Yeah.
That's straightforward. And you get back the two original fermions. However, what in the game that you showed us with the 4 fermions, what you end up doing is to take the combination of psi L for one fermion and psi L for another fermion.
Yeah. So they don't have to recombine into the original fermion. Like you can just take any two Majoranas and make a normal fermion out of them. So yeah, exactly. We use that freedom to kind of, completely rearrange things, to fuse Majoranas into different fermions than the ones we started out with.
Okay, and I can see that in this case, you will have entanglement between the two pairs.
Yeah.
But isn't there an easier way to entangle particles? Why are we going through this whole process?
Yes, exactly. There's a really cool reason for it. Yeah, as we'll see. I mean, ultimately where we're going is that, just to give away the joke in a sense, the punchline, this is going to be our left black hole, and this is going to be our right black hole, okay? And, this entanglement is going to be like, the entanglement between the left and the right side. And the number operator of these original fermions is going to be something we're going to call a size operator, for reasons we'll see. And this is the coupling between the two sides. In other words, in the qubit model, the coupling between the two sides is e to the ig v. And that v was like z operators on both sides. In this model, the wormhole is made out of like left side, right side entangled. And the coupling is given by the number operator of these original fermions. So you actually use both pictures here. This is like the two black holes, and this is the coupling between them, the number operator of the original fermions. And that's what makes this a model so cool, basically, as we'll see.
I agree with you that it is cool. What I don't understand is, where do the black holes come in? I have a bunch of fermions.
Yeah. So that's
holes.
Right. So, we haven't actually talked about the SYK part. So as we'll see, to give away the punchline again, an SYK model is basically four-way or four local interactions between Majorana fermions. And so we're going to get a SYK type Hamiltonian, which is, as I say, is going to consist of like a sum of terms, each involving four Majoranas. And that's going to be, in general, a scrambling Hamiltonian like we like for black holes. And, we're going to have, one being sort of something like the transpose of the other on the left and the right. And so that's what's going to give us the black hole part.
Matt, is this in the same paper that you gave us the link for? Because there's a section, I was just looking for, there's a section called teleportation by size. Is that what we're...
Well, yes. So, that's why I call it the size operator. Yes, like
right.
It was first, I think, investigated in this context. And that's why they call it.
But are you using that same paper for reference, or is there another paper that...
There's not really... Yeah, there's not enough in that paper to reconstruct everything I'm talking about here. There's several other papers that I'll send out links to. That one paper is mainly qubit based. In some of the references, you'll be able to find this kind of stuff. And I have some things in mind that I'll send out. So why do we say a size operator? Why do we call it a size operator? Okay, so this is cool. We know look at that little misspelling right there. We know from like in qubit world, like we talked about the other week, when we were talking about the variational quantum eigensolver and other times too, that we can form a basis for operators on qubits in terms of Pauli's, right? We can take all possible, strings of Pauli operators, ZXY, YYZ, IIX, like all of those that act on, say, n qubits. And we go through all those operators, they will form a basis for the space of all the operators on the qubits in that 2 to the n dimensional space. And that turns out to be super useful. In Majorana fermion world, something very, very similar happens. If we have n Majorana fermions, and we consider taking like all possible, basically like strings of Majoranas. So we have like, Majorana, psi 2, we have like psi 0 times psi 1, et cetera, et cetera, et cetera. Then these also form an operator basis. So we can decompose, any operator into a linear combination of strings of Majoranas, strings of Majorana operators multiplied together. Okay? Now, here's sort of the upshot of that. I hope I can say this part right. It's like a little bit tricky to say. Here we have 4 fermions, right? Say n here is 4. 4 fermions. We split them into 2 left fermions and 2 right fermions. Okay. But actually, let's just consider the left part, okay? We have 4 Majoranas for them, okay? Suppose we had an operator that, here, actually, I want to do this on the, look at the whiteboard. Okay. So suppose we have some operator that acts on these guys, on just the left part. So in this case, it just acts on like two normal fermions. We could take this operator and decompose it in the basis of like 4 Majoranas. So we get all the different strings of Majoranas, this one and like this one times this one and this one times this one times this one, go through all those, take the trace of our operator with all of those things and expand this operator in that basis. Okay. So in this case, like this is an operator that acts on 2 fermions. So we can expand it in a basis of 4 Majoranas and get a bunch of coefficients. So, you know, what we can then do is take an operator and use those coefficients to upgrade it so it acts on just this part. Sorry if that's like a little confusing to say. Like, ignore this picture completely for a second. We have just 4 Majoranas, that's it. And we have an operator. And we expand it in the Majorana basis. Then we return to this picture. We have 4 Majoranas. In fact, they're 4 Majoranas, and then there's these other 4, and these are like related in this particular way because of this whole thing. And then we can like upgrade a given operator that acts on, you know, that is built out of like any 4 Majoranas to be built out of these 4 Majoranas specifically. In other words, normally it's easy to say, oh, you have an operator and you want to like upgrade it to act on like the left qubit. So you do operator tensor the identity. You could do like operator identity tensor the operator, that the operator acts on the right qubit. What I just said is just like a fancier way of saying that. In other words, we can take an operator, expand it in the Majorana basis of 4 Majoranas, and then use those coefficients to upgrade that operator into an operator that acts just on this half of this left-right system, okay? Now, when we were discussing teleportation, I mentioned this fact that like if we had, like what was it, right? We had up, up, minus down, down. I want to move this over a little bit. Right, we had this situation. And we said, oh, like, that's just the same as that situation where we have just like this operator, this entangled, you know, projection or whatever. And I said something like, you take this, like an operator, 1001, when this guy hits this, this state becomes 1, 0, 0, negative 1. In other words, up, up, minus down, down. In other words, we had this idea that we can kind of trade off between states and operators using cups and caps. If I have like an entangled state and this operator comes in, what I end up with, I could look at that equivalently as like that operator literally as a state, okay? Now here's the thing. That's exactly what's gonna happen in this case with the Majoranas, but just like in a sort of more sophisticated scheme. We take an operator that acts, that's like, you know, we decompose it, say in a basis of like 4 Majoranas, upgrade it to act on these 4 Majoranas, where there's like a left and a right. We started off with these in the vacuum state. So these two fermions, they're entangled left-right. So this is like our cup. We act with an operator on the left, and it gets splayed out as a state across left and right. And now here's the really cool thing. If we then look at the expectation value of this size operator, the size operator, which is the number operator of the original fermions, it counts the number of fermion operators in the operator we acted on the left with. So like, let's see how that works. So, right, so let me say it like this. So I have some operator. What was it? I just created like a random unitary operator, okay, computationally. And I have this function size. So what does it do? It takes this operator, okay, and it decomposes it into this Majorana basis of, say, like in this example, for 4 Majoranas. Then we upgrade it, like we get an operator back where like now the 4 operators it's built out of are like these 4 operators, like the left ones. Sorry, but it's just confusing to say. I don't know how to put it. It's like, here literally I take, okay, I create, yeah, well, just to stick with this example, you create like 2 fermions, split them into 4 Majoranas, and those 4 Majorana operators I'm calling M underscore. So I expand the operator in the M underscore basis. But then I also have ML. ML are the left Majoranas in this picture. So then I upgrade the operator, you know, I just multiply each of those by the coefficients obtained here. So then I've upgraded my operator to just act on, you know, to basically be built out of these left fermions. I then act with it on the vacuum state of the original fermions, which is I here. And then I take the expectation value of the number operator of the original fermions. And what happens? So suppose we look at the size of this operator. It's just built out of 1 fermion operator, the 0th one. And we look, the expectation value of the size operator is 1. We look at the expectation value of the size operator of M0 times M1. That's a product of 2 Majoranas. And so the size is 2. Here we have product of 3 Majoranas. And this expectation value of the size operator is 3. Furthermore, if we look at the individual expectation values, say of like this fermion, this fermion, this fermion, this fermion, it'll tell us like literally the number of which Majorana. In other words, here we have a product of Majorana 0, Majorana 1, Majorana 1, Majorana 2. We ask after what's the expectation value of this number operator of the complex fermion, and it's like, oh yeah, there's 1 of the 0 guys here. How many of the 1 Majoranas are on there? Oh, 1. How many of the 2s are there? Oh, 1. And indeed, it makes sense because the overall number operator of these complex fermions is just the sum of the number operator here. So I apologize for perhaps saying this in a somewhat circuitous way, but the point is basically that similarly to the case where we have, we were just thinking about qubits and the cups and the caps, we can, you know, and maybe it's even better, like for some reason I keep drawing it like in the adjoint picture, which maybe is like not the best idea. we have a cup like this, and say, then there's like an operator like that. This is equivalent to if we just started out with that state. In other words, up, up, minus, down, down. Oh, wait. Am I on the, I gotta turn off the screen sharing. Okay, sorry, my apologies. We have a cup, and then we act with this little operator. That's completely equivalent to if we just started out with this state, up, up, minus, down, down. And in fact, the state that's relevant is just 1, 0, 0, negative 1, which is just literally this matrix as a vector. We do a similar thing here, where now this is, left fermions, right fermions, they're entangled. We act with an operator built out of Majorana on the left, and that ends up giving us some state, okay? And then the fascinating thing is that if we take the expectation value, I'll just like draw it like that for like no reason, of left and right, take the expectation value of the number operator of the original complex fermions, this will tell us the number of Majorana operators that were multiplied together to give this guy. It's kind of weird, okay? I just want to keep repeating it because like this part is like, this is like the whole reason that we even want to use Majoranas here, because they have this like beautiful notion of like a literal size operator, literally an operator that's like sensitive, in some sense to the complexity of an operator, like how many Majorana operators have had to be multiplied together to give you, this operator. I mean, something similar is true about the Pauli basis, right? You could say like the complexity of an operator and the Pauli basis is like the number of, you like expand an operator in the Pauli basis and you look at like how many of those operators are just, have a bunch of identities in them. And the fewer identities, like the more, the more complex it is. Here, it's like the interpretation is like even more exact, because in the Pauli case, it's not really like there's an operator who's like literally, you literally take the expectation value and it literally tells you like the number of operators of a certain type that were multiplied together to give you that operator. But in this case, that's exactly what we can do. The ZZ coupling that they use in the qubit picture is sort of just trying to approximate this. So again, just to repeat it, because this is such a nice point, right? It's like we have 4 complex fermions, 4 normal fermions. We split them each into pairs of Majoranas, left and right. Gather up the left Majoranas, gather up the right Majoranas, and then we have this like left side. We can combine them into 2, new fermions, 2 new fermions. We have a left side and a right side, and these are going to be entangled. If we then take an operator that just is built out of left fermions, and we act with it on this entangled state, which again is the vacuum state of the number operator of the original fermions, then if we look at the expectation value of this number operator on that state, which we got by acting with the guy on the left on that original vacuum state, which is an entangled state from this perspective, then that expectation value tells us basically the size of the operator, the number of Majorana operators that had to be multiplied together to give you that operator.
One question here, a little bit confused.
Mm-hmm.
With talk about the vacuum state here. You talk about 4 fermions sitting in an otherwise vacuum state, or the vacuum state of the 4 vacuums, the 4 fermions make up what you call the vacuum state.
So the 4 original fermions, that's the vacuum state we're talking about. So 0, 0, 0, 0 here. That state of 0 complex fermions up here is a state of like a non-zero number of these fermions, and it's entangled between left and right. We then act with some operator on the left on that vacuum state, which is maximally entangled from this perspective. And the expectation value of this operator tells us the size of the operator that we acted on the left with.
So initially, when you have the normal fermions, the vacuum state is a state that does not have any fermions at all in it.
Yeah,
Okay, so you have a state that has no fermions at all, but then you say, well, if I had 4 fermions, then I could decompose each one of them into 2 Majorana fermions.
yeah, exactly. Sure. Yeah, you take the, yeah, again, you know, it's like each one of these has a creation and annihilation operator associated with it. And then we, you know, psi L and psi R are just linear combinations of the creation and annihilation operators of these guys. So we form these linear combinations, we get left to right, left to right, left to right. And then we just take all the left ones and all the right ones. And then, you know, we can, you know, take linear combinations of these to get like new fermion operators. And you look and like they're entangled across left and right. But again, you know, it's like this operator here, 1, what's it built out of? It's built out of this guy and this guy. This guy is built out of this guy and this guy. So, you know, each one of these original guys is built out of something on the left and something on the right. And, you know, basically, you know, it's like to the extent that this works, it's because it's like we're saying, like when we, you know, like again, to go back to the qubit case,
And again, you cannot see
oh yeah, duh, sorry.
better.
Yeah, I'll emphasize this again, right? This one complex fermion here is built out of this guy and this guy. One guy on the left, one guy on the right. This complex fermion is built out of this guy and this guy. So each one of these guys is like built out of something on the left and something on the right. And in fact, like, you know, the first one on the left, first one on the right. Second one on the left, second one on the right. And so, you know, this number operator here for this guy counts the number of 1 fermions, 1 Majoranas in the operator that you act on the left with. And, you know, to the extent that like there's a piece on the left, piece on the right, you can see how it kind of works if you like think about the qubit case, right? Because it's like you got maximally entangled state. Here's this operator we're acting with on the left. And then that's equivalent to starting out, as I say, with this state, 1, 0, 0, -1, right? Which like has a piece on the left, piece on the right. And, you know, the amazing thing in the Majorana case is that then we have like these operators which tell us the number of Majoranas. So again, just to emphasize that, like, let me go back to the screen. So,
Matthew, for the vacuum case, when you look at the complex fermions, for the case of the vacuum, n is equal to 0.
Yes. So n equals 0. But again, we act with the operator that's built out of left fermions, and then take the expectation value. So you see here, we take our operator, decompose it in terms of Majoranas, upgrade it to act with the left Majoranas, apply it to the vacuum state. Then we take that state and we take the expectation value of the original number operator. And that's the size. So as you see here, we have M0, M1, M2, an operator that's a product of 3 Majoranas, and the expectation value of the size operator is 3, 2, and 1, and so forth. And indeed, looking at the individual, so like we could just change this, like let's do another. Let's add that. Well, you can't have, if you multiply 2 of them together, they kind of cancel out. Wait, what if yeah, there's some other subtleties there. Yeah, why does that happen? I forget why. There's a cool reason for that. Let's not dwell on that at the moment. I'll come back on. I'll come to talk more about that next week.
That probably has to do with commutation, intercommutation.
Yeah, exactly. Like well, because remember, the Majoranas are their own antiparticle. So if you take 2 Majoranas, you multiply them together, they're gonna cancel out. So there's that. Which maybe makes the appearance of these size operators like less surprising if you think about it. But in any case, so that's the beauty of the size operator. And in the context of the black hole thing, or the wormhole thing, as I say, the left and the right here model the left black hole and the right black hole, which are entangled, and the size operator is used as the coupling. And so, you know, the intuition here, right, is what? You throw something into the black hole, and what happens? It gets like scrambled out over the black hole. So, you know, if you started off, like think in operator terms, you start off with like a simple operator. Under the black hole evolution, it's going to turn into a complicated operator. If the original operator is built out of like 1 fermion, after it gets scrambled out, it's going to be like built out of like a bunch of fermions. If you then have a coupling between left and right that is sensitive to the size, in other words, it treats size as like the different sectors that it leaves invariant. You see what I mean? Then it's going to sort of couple the left and right in a way that respects size, respects the difference between simple and complex. And then once you've coupled it, what happens on the right? It's basically, remember the Hamiltonian is just, in the qubit case, the transpose of the original one. So this other Hamiltonian just sort of unscrambles the egg, and like the original message has been transmitted successfully precisely because the coupling was provided by an operator that sort of treats, you know, things of different complexity appropriately. That makes sense. What to say about that? Something else. Oh yeah, one other important thing. I should say. So in string diagram world, right, we have cup, and then we have an operator A, right? And what we can do, obviously, is take this operator A and drag it around to the other side. Now, like in the case of teleportation, right? We had that. So we could take this operator and be like, oh, I'm going to drag it around and pop it over here. So what would that look like? You know, at the end of the day, it looks like that. And so, like, that's a really important thing about entanglement. In other words, you get the same state, like, if you act with A over here, and then, like, make them do this measurement, or if you act with A at the end. In terms of teleportation, it makes sense, right? You could, like, have a qubit you're going to teleport and, like, apply an operation to it and then teleport it, or you could teleport it and then apply the operation. Doesn't make a difference, it's the same thing. But what about in the middle? The point is that this is going to be A transpose. So another way of saying it is, well, and this is kind of more fun, right? You could take your qubit, take this entangled particle, right? One of these entangled particles, act with the transpose of A, and that's just the same thing as like acting with A here, or acting with A here. Instead of acting on the qubit you're about to teleport, or acting on the qubit you did teleport, you could act on the entangled particle that you're using to teleport with the transpose. And kind of the...
I have a question here.
Mhm.
If you take this diagram and you stretch it into a straight line, into a straight vertical line, in one case, you are going to have the operator. In the other case, we'll have the transpose of the operator along the vertical line.
But would you though? Like think about like if you literally did this with a string, right?
Yeah.
When you pull the string, this goes like that. All right, like this will turn like that.
Okay.
You see? That's why it's the beauty of the string. Like it really is like a string.
Oh, that's neat.
Yeah, totally.
Neat. I like it.
So so we got this transpose thing going on. So, you know, the point is basically that is the same thing as that. We can move things around the bend, but we have to take the transpose. So that's true, you know, in the world of the qubits and that we would normally talk about here. In the Majorana case, it's sort of interesting. Instead of taking the transpose, you just take the operator times I. So this is kind of cool. So like I have here an operator O. I decompose it in terms of Majoranas, and I upgrade it to act with the left Majoranas. Alternatively, I take the operator and then upgrade it to act on I times the right Majoranas. And they're the same thing. So that's just the equivalent of like this equation. But instead of taking the transpose of the operator, I just take I times the operator. This is sort of interesting, right? So like what normally would be a matrix transpose in this Majorana world turns out to be just, I mean, it's funny. It's like instead of taking the matrix and like turning the matrix like 90 degrees or like swapping the rows in the columns, taking the transpose, instead in this case, you just do a 90-degree rotation like in the complex plane. You just multiply it by I. And in a way, the intuition makes sense because each of the original fermions has a left and a right part. And so you can think about it like left and right are sort of just separated by, you know, a rotation of this guy, so to speak, a little complex rotation because each one of these guys has a left and a right part. So that's Good to know. How are we doing on time? This might be a good moment to stop in a way. There's a couple more things we have to talk about, just like literally the SYK model, which is like here, as I say, a fourfold interaction of Majoranas. And then we have to sort of talk a little bit about what it means to like insert the qubit. And then I have like some cool visualizations, but maybe we should leave that for next time. Because,
Okay, Matthew, on the issue of time, on the one hand, this is so interesting. I wouldn't mind if it goes on for hours and hours.
I mean, I love talking. Like I can keep going.
And my brain is not up to the task. My brain just stops functioning after 2 hours. That's it. And
Yeah,
then
for real. It's only human.
Yeah. In my case, unfortunately, this is very true, a very limited human. So I wouldn't mind if next time you start by reviewing a little bit what you covered during the last half hour or so.
Definitely. Yeah,
Now,
yeah. I'll review this construction and how we get the size operator, and it'll be good.
My guess, and I guess you're going to hear some more about it, is when you talk about the left Majoranas and right Majoranas forming two entangled black holes. I guess that, again, this is just some sort of form of speech, some analogy between the Majorana groups and black holes. We don't mean to say that the Majorana fermions form a Schwarzschild black hole. I do
Right.
not
So,
anything about to suggest it.
yeah, so again, like the only thing that makes it a black hole model is like this, right? So here's the SYK Hamiltonian. Like you choose some, coefficients and take a sum over quadruples of Majoranas. And so, this would be like what we're taking to be the black hole Hamiltonian on one of the sides. And then, the Hamiltonian on the right would just be like I times that. Whereas before in the qubit model, we took the transpose of the Hamiltonian. And to the extent that this disposed model wormhole, people like it because this SYK model is like fast scrambling. Because of this interaction, shit gets scrambled very, very quickly. And so that's the sense in which it models a black hole. But yeah, like not just any, in order to even get that, you have to specify the dynamics. And none of that, follows from this. Like this is just the mechanics of how Majoranas work. And there's like this interesting way of building a size operator. But yeah, this is not the black hole part specifically.
What does SYK stand for?
Yeah, Sadev, Ye, and Katayev. Sakdev. Just names.
Okay.
Yeah.
You know something? When you Google SYK connector, it's a pipe connector.
Really now?
Yeah, for those of you out there who are plumbers,
Oh,
an SYK. Yeah, no, that's
battery cable.
SYK cable.
it's a gas pipe connector. I mean, I didn't know that, but I know it stands for the three physicists.
Yeah. Well, what does it stand for in this case?
I don't know. Oh, it's also a power cable, but it's also a gas pipe connector. That's what I came up with when I Googled it.
That's funny.
That's SKY. No, that's.
Oh, this one. Oh, this one you mean?
I don't know why different stuff is. Oh, you Googled SKY. You didn't Google SYK.
Okay. The sky connector.
SYK. Now it's a battery cable. I got a pipe connector, and I was trying to figure out what it stood for. It may be a trade name.
Oh, like this kind of.
I know it's sold by Granger, but it's a trade. Oh, hey, pipe and fittings.
There you go.
Scroll back a little. Pipe fittings. Yeah, pipe and fittings at Home Depot.
Yeah, I mean it's appropriate because I mean I do think of these string diagrams like also being like two.
Okay, now it
carrying-
makes sense.
By the way, you can also buy entangled black holes at Home Depot.
Yeah.
No,
Oh,
black
But
pipe.
you have to be very high when you go there, or else they won't sell it to you.
uh,
There it is. I don't know what it stands for.
I have a question. Can you so you can simulate a black hole with a scrambler operation, and so what are the properties of this scrambling? Does it like have to be like perfect scrambling, takes away all possible information, or something like that?
Yeah, right. Like some of the papers provide, like a more like a quantitative measure of like, how fast does this given Hamiltonian, scramble operators. But yeah, I mean, my intuition for it is that, yeah, rapidly like an operator which is like localized becomes, kind of delocalized, kind of bits and pieces of it, or, now kind of at all different scales. Um, and then if you think about the idea, like in the ADS CFT correspondence, like the CFT conformal field theory, I mean, that's like a, basically kind of a scale invariant thing. In other words, something which sort of has similar dynamics at every scale. And so there's, yeah, definitely a relation there. But yeah, for next time, I'll look that up. There's different, like measures that people use to sort of like diagnose how fast or how well certain things scramble. And yeah, like in the paper they talk about this idea of like perfect size winding. And yeah, I mean it's sort of basically like the idea being that if you have like a size operator and if you have a Hamiltonian that is like scrambling and has perfect size winding, then you can do the coupling. The coupling essentially consists of doing like just a phase rotation in the basis organized by size. That makes sense. I think that's right.
Okay, and another question is, does the scrambler work the same way every time, or does it scramble, is it random?
Let me tell you what is my guess of what we mean here by maximum scrambling. My guess, the way I view it, is the following. Suppose you have a bunch of particles sitting, and you have a new particle coming in, and this is the particle that is going to get scrambled. It carries some information. In usual quantum field theory, in usual elementary particles, what happens? A particle comes in, it interacts with one particle, and there's some consequence, some results, the output of this interaction. So now the information that was in the initial particle is contained in the, let's say, two particles that came out of the interaction. Each one of those two interacts with another one. And so now the information will be distributed between more and more and more particles. Now, on the other hand, if instead of having just 3-point interaction, you have 4-point interaction, 6-point interaction, 1,000-point interaction, then with one single interaction, the information that came in can be distributed amongst any number of particles coming out of the interaction. And this is my guess of why we have this SYK Hamiltonian, which is a 4-point Hamiltonian as opposed to a 3-point interaction, which is what we usually have, like in a Yukawa interaction. But this is just a guess on my part.
I'm going to send this paper. This is a nice one. Quantum epidemiology, so relevant these days. Operator growth, thermal effects, and SYK. And they review, many of these things that I was talking about. They even have some similar pictures.
Put the link on the chat. You can
Yeah.
do it.
Chat. But at some point, I remember there being like some kind of picture in here that I'm thinking of. The upshot was something like you can, model sort of like operator growth, like an epidemic, in the sense that, if you're imagining like qubits, you have a bunch of qubits coming in, and then, it's like, say, these interact, and then, these interact, and then, these interact, and then like, those interact or whatever. All this stuff is basically going to could be modeled with like some big unitary operator. But you could sort of decompose it into these like pairwise interactions, for example. And, you could think about that like in terms of, each one of these has the potential to create entanglement. It's kind of like, disease like spreading through a system or whatever. And so the idea is like fast scrambling, evolution is basically going to have, the coronavirus is going to spread as quickly as possible among the population, basically. It's like the concept there, yeah.
I had another question, and that was scalability. It seems like so far you've just talked about transmitting 2 bits, and then to scale it, it seems like you can scale it in time. In other words, use the machine over and over again and get a lot of bits that way. Or you could scale it by entangling more particles.
Yeah, right. So, like in the teleportation thing, if you have not just, an entangled pair, but, several entangled pairs, many entangled pairs, you can transmit much larger states. And yeah, I mean.
Wait, do they have to be pairs, or could all the particles be entangled together?
It could be both.
Oh.
I mean, in some ways, like, yeah, they're equivalent cases. Yeah, and for that matter too, I mean, it's like the model that I'm eventually going to show, like that I run on my laptop, is very bad. I mean, it doesn't really work that well. I mean, because in the end, I use just a mere handful of fermions, basically. And when people actually analyze this stuff, like they don't do these kinds of simulations. Generally, they do things like imagine the SYK model and some limit where you have like a fuck ton of like fermions. And, you can draw these like crazy diagrams called like melon diagrams. And, take these sort of like limits and like examine like the behavior of the SYK model where, there's, instead of 4, there's like, infinite number or something basically. And, or just a large number. And then they can prove various things about like how good the teleportation or the wormhole is in that case. But yeah, like certainly it's like in the stuff I'm going to be showing, it's like it's very small scale. And certainly, for the time being, I guess if you're going to use a quantum computer, maybe don't have that many qubits.
Yeah. Okay. So I was thinking of practical applications, believe it or not, and I was thinking of banks, need to pass to each other their book of cryptography, like a one-time book of cryptograms. So if Alice has a book, she shouldn't look at it until she's going to transmit it to Bob. And then they can transmit it that way because of what Moshe said. they can transmit the classical. But I mean, classically, Alice will check to see what the result was and then transmit that to Bob, and Bob will then get the book, and neither of them knows what's in the book. Well, Bob can use it on his side, but then that's the way it will be done. I mean, if you're trying to use it in a practical application.
Yeah, I mean, to some extent, scrambling it's like encrypting, basically. It's like quantum encryption. And,
But
the
quantum encryption can't be broken into with a middleman.
oh, sure. I mean it in a different sense. Like, yeah. Like those
Oh.
encryption protocols, like that's certainly true.
No,
But,
Marty, you're absolutely right. This would be an application. There doesn't even need to be an Alice. There only needs to be somebody on the receiving end, receiving what's being transmitted.
Oh, yeah.
And if somebody tries to intercept it, it's gibberish because they haven't been given the Bell state.
Yeah.
But the
I was thinking that Alice and Bob could be robots.
oh, absolutely, yeah. Alice and Bob are just figurative. Of course, they could be robots.
robots, yeah. Yeah, I mean, and for that matter, it's like in the case of these black holes, it's sort of interesting. You have these two-sided black holes, and like the time evolution on the one is like the transpose of the time evolution on the other one. And in the case of the and so that's what allows the message to kind of like unscramble. So I mean, like, even besides like the normal, like I'm saying, like the normal quantum cryptography stuff, just at the level of like, I could take a quantum state and I could scramble it, and me and my friend have like agreed upon what Hamiltonian I use to to scramble it. So I mean, and that's in a sense just a statement about the fact that, like, if you have a quantum computer, evolving forward in time is no harder than evolving backwards in time. You're just implementing, e to the IH versus e to the negative IH. Like if you can do either one, I mean, in the case of a quantum computer, it's like going forward in time is as easy as going backwards in time. That's what the kind of control gives you. In real life, you'd have to like create these situations where, like, by luck, as luck would have it, the time evolution of the one is basically the reverse of the other.
Well, that's unitarity.
Yeah, that's unitary.
But actually, it's logically the grandfather paradox, which I jokingly discussed before.
Well, again, I mean it in the sense of being able to crack an egg, take a broken egg and bring it back to a.
Well, that is theoretically possible, but
that's what you can
go back in time is not logically consistent because, like I said, I could go. The grandfather paradox is you can go back and kill your grandfather before he reaches puberty, and then there's no way you could be here. So how the hell did you go back and you weren't here to begin with? It's a logical inconsistency.
Yeah, and incidentally, it's like when you think about the string diagrams. I don't know if this actually is good. I mean, it's like, it's sort of an interesting thing, right? It's like talking about this. Well, like, okay, supposedly like this goes in, and I'm saying, oh, maybe you can interpret going around this bend. It's going backwards in time and kind of sliding across space, going forward in time. So, I mean, what would be like what would be a closed time-like curve in this case, right? It's be like a circle, right? Like you take an entangled state.
You can't have a closed time curve.
You measure it in this state, and if these, like, that's just, it's a scalar. Like in tensor diagrams, when you have a closed diagram, that just gives you a scalar. In other words, like an amplitude, right? That we start out with the maximally entangled state, and that we end in that maximally entangled state.
But you can't have a closed time curve.
I get it, but I'm just saying, like, if we playing around with these diagrams, like what would be
What did Moshe wanted to say something?
The grandfather paradox. Let me make it a little bit more subtle even. Well, there's no way you can go backwards in time. But suppose you had the possibility of sending information backwards in time. You could send a message to your grandfather before he reached puberty, telling him not to marry your grandmother. For instance, suppose that you could send your grandfather your picture. You take a selfie, you send it to your grandfather, your grandfather takes a look at it and says, oh, I'm not going to marry Michael's grandmother.
All right, but here's the thing, Moshe. To send information, you have to send energy. And this is the whole point of not being able to communicate faster than light. Because to send information any way we know how, you have to send energy. And you can't send energy back in time. Sending information means sending energy. Now, with entanglement, there's no energy transfer. That's why you can do that. You can't send that. You can't send that energy information.
That's the point.
That is the point.
Information transfer without any energy transfer.
But just logically, you could explain this to anybody, you know, who doesn't know physics. You can't go back in time and change history because you wouldn't be here if you did that. So how can you go back if you wouldn't be here in the first place?
Yeah, I mean, the thought I have is like, thinking more about the teleportation thing. It's like, you know, like I'm saying, like if you don't have this part of the diagram, this guy comes in, like there's some state here. It goes back in time, but like there's no way for you to access it unless you have this like entangled pair. And then, you know, this comes out here. But again,
No, but even an entangled pair cannot be acausal. It's still causal, faster than the speed of light, but still causal.
Sure. Yeah. I don't disagree.
In other words, it can happen instantaneously. It's still causal, but to go back in time for B to happen before A when A causes B, just is logically inconsistent, to say nothing of physics.
Right. Well, okay, wait, but what I want to say is this: like, if you look at the history of this thing, right, and like that's like some kind of measurement here, right? You have like, you know, at this moment, time's flowing forward. This measurement hasn't been made yet. But suppose we measure this first, right? As opposed to the case where we normally think about teleportation, right? When we normally think about teleportation, it's like this, right? It's like state comes in, you know, Bob or Alice makes the measurement,
right?
And then, oh, over here, we like make some measurements, we figure out, oh yeah, that's the same state that went in there.
Matthew, the answer to that is that if the two entities are space-like separated, as opposed to time-like separated. Does everybody understand what the difference is?
Yeah.
If they're space-like separated, there's no way to determine which pair of an entangled
totally
pair you measured first, because you don't know which, because time doesn't have any meaning in space-like separation. So there's no way to determine which was measured first.
Yeah, so in a way, in this picture, you could look at it like the state that comes out here is like affected by the outcome of like this measurement.
No, it's the other way around. The state that comes out, if you measure that first, it's affecting the one that you...
If instead you make this measurement and then later on do this, it would be like the result you get for this measurement is influencing the result you get here.
Yeah, but that's forward time.
Yeah, it's completely...
it's forward time. There's no way to go back in time.
Sure. I just thought it was...
Time-like or space-like separation. So you can't necessarily determine which measurement was measured first. But that means you can't determine the time that each was measured. But
Yeah,
believe
I
me,
agree with you
there's no
completely.
way. It's got to be causal. It can't be acausal.
Yeah, yeah. No, I mean, I agree with what you say. Yeah, I wasn't giving this as an example of like time travel or whatever, but just
Well, you can time travel into the future, but you can't time travel into the past.
Yeah, we're doing it now.
Traveling into the past or
No, the
the future?
future.
'Cause it's 706.
well,
Yeah.
I guess, but the thing is, like, maybe that's it. I would say about this picture, right? Is like, if you do this, like, here's a measurement. It's like you're tempted to think of it like the state goes around like that. Yes.
But you're confusing math with reality.
This, it's like this
Oh.
hasn't happened yet, and so I don't know. It's just interesting to.
But if you measure B first, then it affects A. You know, it's not that you're just assuming A is measured
Right. But I guess,
present and B is in the future. Not if you measure B first.
you know, I guess the paradox is that, so to speak, and maybe it's not really a paradox, is like in this picture, it's like you're like, oh yeah, you know, we started off with the cup, we measured this to be in the cap state, and so then of course this thing did this weird whatever you want to call that and popped out here. But
Paradox. That's two heart surgeons, right? Paradox. That's like a paradigm. 20 cents.
Oh,
Bad jokes. Okay. Marty doesn't like my jokes. Okay.
just groaning. No, it's okay.
but like in this case, you could say, like, you know, this result of this measurement has to affect the probabilities for this. So it's like something's kind of coming up here. But then again, we're still free to choose what happens here, right? It's like, what if we decide not to measure those? We just measure that, and it's like meaningless, right? You see what I mean? It's like, this is just an entangled pair, and we make this measurement and get something completely random, and like whatever. But then later on, if we choose to do the Bell measurement,
Yeah.
we in retrospect reinterpret this as being like this teleported qubit. Like, it's kind of funny. I mean, you see what I mean? Like,
Right. It works.
sort of weirdly time symmetric.
So.
Not really. Only mathematically. You do a lot of stuff with math that doesn't correspond to physical reality.
Well, I like the diagrams. I'll tell you. I mean, they stuff that like, you know.
But the diagrams correspond to actual quantum gates and
Yeah.
when they're implemented. And you can't go back in time through a quantum gate.
You know, you're right that in some ways it's just math.
Yeah.
But
Math is great when it describes physics, but when it doesn't describe physics, then it's not, you can't just say it you know, it's so. It's so on paper, but not in reality. You don't know
well,
you don't know Barry McFarland, do you? Who's the founder of the New York? Oh yeah, well you've been to the.
Yeah, a little bit. I
don't know why he doesn't come to your. I mean, he would be interested in all this crap.
Well,
because he's
I
first
don't know.
and
Yeah,
foremost.
I don't think he's ever been to ours.
He never has. He's first and foremost a mathematician, and if something is borne out mathematically, then there has to be a physical equivalence.
Huh.
And he, you know, he gets very upset if you try to argue that point.
That's funny.
You know, he says all these. My contention is all these mathematical theorists who dream up with these great theories. You know, until there's some correlation to physical reality, until there's empirical evidence, it isn't physics. It's just theoretical math.
What I would say about the string
He
diagrams,
explodes when you say that to him.
the thing that's cool about the string diagrams, though, is that, like, at least for finite dimensional quantum mechanics, you know, the string diagrams have been proven to be complete for finite dimensional quantum mechanics. In other words, like anything you can do with the diagrams corresponds to something true you can do in the physics.
Because you can implement it with quantum gates.
Yeah, yeah. And you know, the benefit I think, you know, like Bob Coca would say is that, you know, the logic of like entanglement and tensor products is intrinsically two-dimensional. It makes much more sense on the plane.
Wait, what is that? What's two-dimensional?
The logic of
Okay.
entanglement and tensor products and stuff.
Well, you know, now they're doing stuff experimentally two-dimensionally with graphene.
Well, sure, but I mean it almost in a
A lot
different.
of stuff going on experimentally in 2 dimensions.
I mean it in a sort of a different sense that, like, algebraically, we're often writing things like A tensor the identity times B tensor C acting on like this state or like whatever. Like, in other words, we write out like what we're doing in algebra, and algebra is linear. You see, you have to write it all out
Right.
in a line. But actually it makes much more sense to be like, oh, like suppose this was like the entangled state. Oh, that's this. A tensor the identity. That's just A tensor like nothing over here. And then B and C is just this guy. This comes in like that. In other words, the logic, like the natural home of things like entangled states and operators and tensor products and stuff, the logic of it like really is like kind of like two-dimensional. And like, you know, having to write things out using our like normal notion of just symbolic algebra where everything has to be on a line is actually like really limiting to the mind. Like you just don't see things at first. It's just like a jumble of symbols.
But you know that physics.
That's really that's what math is really about. Like it's
physics
about
ultimately
clarity, you know?
Physics ultimately is nonlinear. All of our linear physics is based on low energy physics.
Well,
Any branch of physics, when you go to high energies, it's nonlinear.
Again, we're using the word in two different senses, right?
No,
Like,
I know.
yeah. Because I mean, you know, I mean, it's an interesting question, right? Because
why is it two-dimensional is not intuitive? Two-dimensional can be more intuitive than three-dimensional.
Sure. And in fact, I mean, there's, you know, generalizations of these diagrams that are three-dimensional, right? Because, you know, someday we'll have to talk about this. It's like, you know, consider this, right? That's like a swap gate. Swap the 2 qubits.
Right.
And it's like two-dimensional in the sense that this crossing is kind of like irrelevant. But, you know, in actual 3 dimensions, right, it would have to be like either this crosses under that one or this one crosses over that one. And so you could be like, are there, you know, generalizations of string diagrams so that if they really are like, they're called braid diagrams because you're like literally track as if they're in 3D. And yeah, you can use these and they can model like anyons, you know, the fractional,
which are theoretical particles. They have not been discovered.
Oh no, they've done those. Well, that's exactly the ones that they have in the two-dimensional systems that you were talking about. So they create these two-dimensional surfaces, and they're particles such that when their world lines like wind around each other, they remember like how they were wound around each other in the plane, precisely in this sense. Like their world lines get kind of tangled up.
So then anions have been discovered?
Yeah. I mean, yeah, they do this in the lab.
So why do I keep reading that they haven't been discovered yet? I don't know. Maybe an anion is a theoretical explanation for this, but I mean, nobody's isolated any anions.
No, they've done, and in fact, you know, there's attempts to build like quantum computers out of them because, you know, I mean, I don't know about like maybe in like the wild or like whatever, Right. Here we go. This is maybe what you're thinking of. There's different kinds of anyons, and so they found abelian anions.
What kind?
Abelian anyons,
Oh, abelian.
not
Non-abelian.
non-abelian ones.
Okay.
So some kinds have been detected and other kinds not. So we're both right. Nice.
No, I mean, I look, I'm no expert on this. I mean, it's just the stuff I've read is, nobody's discovered them, but I don't know. Maybe certain experiments have interpreted them as, you say anion, I say anion. You say potato, I say patootie.
Patootie. Nice. Yeah, what is the difference between a
potato and a patootie? Most of us are potato heads. The president of the United States is a patootie.
for now.
For those of you who agree with me politically, I know Jamie lives in the Midwest. He may support the guy. I better watch what I say.
The anions do exist as quasi-particles.
Mm-hmm.
Just like phonons exist, they're quasi-particles.
Yeah. And actually, I was reading a cool paper where they do a wormhole made out of anyons.
Then I certainly don't believe in them.
No, it's for real. Yeah, where was that paper?
So would we have to rename the God particle? The God particle. We'd have to call anions God particles, maybe. Who is it? He's Leon Letterman, who discovered a number of the fundamental particles. When they referred, and he had something to do with the Higgs boson, he was looking for it. When they referred to it as the God particle, that he was looking for the God particle, he blew his stack because he was an atheist.
Yeah.
I want them to say that.
Yeah.
The Higgs boson is commonly called the God particle.
I sent this paper to the link to the chat here. Topological wormholes. It's actually a really nicely written paper. Kind of goes into these little, connections, but sort of like how to encode, the anyons, basically in terms of like qubit operators, they kind of basically just like in the same way that we've been doing our wormholes, build a wormhole out of qubits, build a wormhole out of Majorana fermions.
The thing is,
turning the crank, doing the same thing here with.
The thing is, a lot of quantum phenomena can be programmed on a classical computer, but it still doesn't prove anything. Until you program it on an actual quantum computer, which at this stage of development is not easy for a lot of phenomena. Until you actually see it happening on a real quantum computer, we don't know if it's real. We could program a lot of this stuff on a classical computer. We can program quantum phenomena on a classical computer, but we don't know if that corresponds to reality necessarily. Until it's actually an actual quantum computation, and you need more than a 52 quantum bit computer, which apparently is
we're getting there.
Strongest
I mean,
one.
you could do these, like the very shitty kind of simulations that I've done. I mean, you could run them on the quantum computer and see if it,
So does it prove anions or
yeah,
wormholes or I don't know.
Did they do this? I wonder if they actually did this in the lab or not, or if this is just like sort of how to do it.
As far as I know, there are only 3 organizations that have greater than 50 qubit computers. IBM, Google, and who's the other one?
Well, there's a couple different ones. Rigetti.
And who even knows if they're telling the truth? Google claims that they've calculated some problem that would take 10,000 years. They calculated it in a few minutes. but nobody really knows if they're telling the truth. Well, you know, this stuff is all proprietary.
Yeah. Well, they
And
release,
yeah.
you know, their research or like
And
whatever.
we don't know what governments are doing. I would say the most powerful quantum computers, if they exist, are in the hands of the governments.
Yeah. Well, you wonder about that.
You know,
Yeah,
like the U.S. government and the Chinese government, I would say have, and I'm sure they're doing research on it.
Here,
And
you
what
might
IBM and Google tell you, you can't believe necessarily. And the governments aren't talking.
you know, I have to say that IBM is doing some impressive stuff these days. I saw this on Twitter. I'm like looking for like the actual
Well,
thing.
last week, IBM split into two companies.
How did they?
And after all these years, they finally came to their senses, because when I was your age, Matt, there was only one computer company in the world, IBM, and I worked for them.
Oh, yeah.
And I watched them go down the toilet while I was with them. They refused to face what was happening in the market. And now, you know, in the last few years, they've made some partial comeback.
Well, I mean, it seems, I mean, I don't know anything about IBM really, but like, I mean, I have to say, like the last couple of years, they've just been like their quantum stuff is just like really just flourishing like crazy. I mean, they got this like these community advocate programs, like they got this software, that software, all these quantum computers up to, you know, 20 qubits for free on the cloud. They got like,
well, I think they have a 52 qubit now, but they have had for decades one of the foremost research centers in the world where I worked. But so did Hewlett Packard.
Right.
And they went into the toilet because they didn't know what to do with it. I mean, the scientists who worked at the research center couldn't communicate to the idiots who were running the company. And Carly Fiorina, great businesswoman.
Oh yeah.
Who rose from a stenographer to chairman of the board of Hewlett Packard.
Huh.
That's not the person you want running a technology company. Somebody who rose through the ranks from secretary. You know, you need a technologist to run the company.
It's impressive, but yeah, I mean, it is sort of like, you got to be a little bit of an engineer to run a tech company.
You got to be an engineer, and now you got to be a physicist and an engineer and a business person. But even in those days, and in the early days, it was always an engineer who ran IBM, and then they started, you know, they hired we called him the cookie cutter. They hired this guy, Lou Gerstner, in the 80s from NBC, not National Broadcasting Company, National Biscuit Company.
Huh.
So we called him the cookie cutter.
Lol.
He freaking destroyed the company. He didn't know what he was doing. And they wouldn't listen to reason about what was happening in the market.
Yeah, it's interesting. I wonder what, if in, you know, the last 10 or 15 years, things have changed there. I wonder what it is.
Well, the only reason IBM survived, the only reason IBM is not bankrupt, defunct, is because they had a cash hoard of several $1 billion.
Yeah,
you know, when $1 billion was real money.
Sure.
And that's what saved them. They say their cash hoard saved because they had a monopoly in the computer business until they were challenged in the 80s. And then it was all downhill. But I worked for all of them. I worked for Xerox too. Xerox. Oh, did I say Hewlett Packard? It was Xerox that had the Palo Alto Research Center. Xerox could have been Microsoft, the Apple, the Google, the everything. They had all the scientists working for them in Palo Alto. And the people who ran the company we called toner heads because they sold copiers to office people. We called them toner heads. And by the time I got there as an electrical engineer, the company was already, you know, gone. But a lot of these companies that have, you know, great research labs, the best research labs in the world, they don't know how to market their products because they have the wrong people running the company. And I'm afraid that's going to happen with, you know, unless Silicon Valley has gotten smart in the last couple of decades, that's going to happen to all of these monopolists. They
Yeah.
get soft. And what monopolists do, and IBM did this for you. What monopolists do, and this is economics, not physics, monopolists thwart innovation because they like to keep the status quo. You know, they had PCs in the 60s. I knew people when I worked at IBM who had developed PCs in the 60s, and the company wouldn't market them
Yeah.
because they knew it would threaten their mainframe business. And this is what happens when you don't have antitrust enforcement, which we don't get from Democratic or Republican administrations. And what happens is you just get a stalemate, and then you get countries like China are going to take over technology.
A comment about antitrust enforcement.
Yeah.
In the late 70s, when I was at Bell Labs, and the government was suing AT&T, eventually they broke up AT&T.
Right.
I saw a note on somebody's door. It said the following: we have two big monopolies in these countries. One gave us the laser, the transistor, and the best telecommunications network in the world.
Right.
The other one gave us inflation, stagnation, and the war in Vietnam. Guess who is going to tell who how to run its business?
Who was the second one, Moshe? There was
The first one gave us the laser, the transistor,
right.
and the best telecommunications network in the world.
Yeah.
The other one gave us inflation, stagnation, and the war in Vietnam.
Who gave us that? The politicians gave us that.
Yeah.
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 Now, and I'll tell you something. AT&T,
who how to run its business.
But AT&T was a regulated monopoly. These other IBM was not a regulated monopoly. And the monopolies today, Facebook, Google, they're not regulated. And I got to tell you, with all the talk, with all the bullshit, they're not going to be regulated in this political environment, Democrat or Republican. You know that Charles Schumer, the leader, the Democratic leader of the Senate,
yeah.
You know that his daughter is an executive at Facebook. So
really?
You tell me, and Schumer has taken hundreds of thousands of dollars, as have Republicans, from Facebook. Zuckerberg goes before Congress and lies through his teeth, and they never call him out on it. They never call him back. That's called perjury in a court of law.
Yeah.
But they talk about it. They give lip service to antitrust. The last antitrust legislation was against Microsoft, right, which was modeled on the antitrust against IBM, which was completely unaffected by the time they brought it because the market was already changing for both IBM and for Microsoft later on. And that's the only way these monopolies, get toppled, when the market changes and they're so soft and entrenched that they don't see it coming. But decades are wasted. Decades of innovation are wasted. To say nothing of the threat to our democracy with social media. That's a whole other issue.
Yeah, I agree with you. Although I will say, I mean, the one thing I feel like that makes some of these monopolies like of today a little different than in the past, at least in terms of like the innovation stuff.
Yeah.
I mean, is like although I do believe that, these large conglomerates sort of, I mean, it changes the whole dynamic of like if you're, trying to do a startup, the incentives are all different and everything.
Oh, forget it. You can't do a startup unless you have the approval of one of these monopolies.
Yeah, but it's interesting how...
Try to go into competition with Jeff Bezos. See what happens to you. He either buys you up if you're buys you out if you're lucky, or he destroys you, and you can't sell your product on his platform.
But on the innovation front, it's interesting to me that so many of these companies are, like, at least now, super invested in open source stuff and the open source community. Like, so many of the, like IBM and stuff. I mean, like a lot of them, I don't know, is Qiskit, like, can you see the source code of it? Like in the, in the 80s and 90s, I mean, it would have been like, all the source code's just like fucking locked up or whatever.
Well,
And
it
I
was
mean,
proprietary at
yeah,
IBM.
but like these days, here's IBM software. It's open source.
But here's the deal.
See, like that, I mean, I'm not saying it's good or bad in terms
You
overall.
develop a commercial application, something to sell to the public. Apple has to approve it. If you can't sell it through the Apple Store,
Yeah, well, fuck Apple. Like Apple's the worst at this. I mean,
of course they are.
And yeah, like how much is Apple release as open source? Like, I mean, compared to like, I mean, it just seems to me in the quantum world, like, IBM stuff is mainly open source, the Xanadu stuff, Rigetti's stuff, like most of it is actually kind of,
Well, that's good for developers, but
yeah, it's good for developers, good for innovation.
Benefits Apple if they decide to let you sell it in their store. But if it competes with one of their products, you're dead.
Yeah, Apple's just they're very close.
How they haven't started antitrust proceedings against Amazon, I can't figure it out. But they're all on the take. The politicians are all on the take. We have a corrupt political system. Both parties don't believe what any of them say.
Yeah, I know.
You can believe probably
it
more
doesn't
what
end
Trump
with,
says than what Biden says.
Yes.
For what that's worth.
Oh, wait, that reminds me though. Did you guys see go to quantum.gov?
Why? Is that a rerun of the dueling town halls or
Yeah.
joke? If you don't know who you're voting for, if you didn't know who you were voting for after the last election,
Yeah, I know.
don't vote, please.
But
Voters.
One thing and a misleading thing to say about Donald Trump is that he was our first quantum president, in the sense that in 2018 he signs a bill into law that like basically established some quantum government program, and they're throwing billions of dollars at it in terms of like,
and if you can figure out how to get his ass stuck in a wormhole,
I'll let you
we
know.
will worship you.
But I thought this was really funny. Like look at their logo, the National Quantum. Oh wait! Let me show my screen. Look at their logo. It's like
there's scientific
quantum coordination,
funding.
National Quantum Coordination Office. It's got an eagle in a cat.
Yeah.
But I think that's really funny actually, because it's kind of subversive, right? Because like if that's supposed to represent America, and you can put America in a cat, well then you could also have a superposition of like different nations. So it's kind of I was wondering like the people behind it, they were thinking about that.
Well, you're not old enough to remember John Lennon.
International state.
You're not old enough to remember John Lennon. John Lennon made a song, "What If There Were No Countries?"
Yeah.
What if there were no countries? If we all cooperated, imagine.
Yeah. What if there was
we would have everlasting life and health and everything else. I mean, this competition, this capitalistic competition.
Yeah.
And don't believe that the Chinese are communists. The Chinese give communism and capitalism a bad name. But capitalism, this competition, we are social animals. We're supposed to cooperate.
Yeah.
That's how we survived up to this point. And because now we're competitive, we're going to destroy each other. We're going to destroy civilization.
I agree. I couldn't agree
That's my, so don't have children.
Yeah, no way.
That's my excuse for not having children. I wouldn't bring a child into this world.
Hey, Michael, that's
Yeah.
a way of destroying civilization.
And by the way, that's why we're the most advanced species in the universe, because once they reach our level of technology, they destroy themselves. So all this crap about searching for ET, in outer space, we've been searching for 70 years. Not a single non-natural signal, because they don't exist. We are the most advanced civilization. And we're on the verge of destruction. 2 minutes to the doomsday clock.
Oh yeah.
Closest to midnight as it has ever been, even closer than during the Cold War.
Yeah, really? That's
well, because during the Cold War there were essentially 2 nuclear powers. Now
Yeah,
You don't
no,
know who's got nuclear weapons. You got
balance.
lunatics, you know, who could have access to it. And they want to bring, like, I'm not going to mention his name. It begins with a T. What if he does lose the election and he says, I'm taking all of you with me?
Well, my favorite thing was like I heard on the news that it's one of his rallies, and you know, you never take these things entirely seriously, but he was like, "Yeah, maybe if I lose, you know, I'll have to leave the country or whatever."
You know
I mean, I
something?
should leave the country, and I was like, "That would be so crazy if he did that." You know, like a week or two before Biden's inauguration, he's just on a plane. He's like,
Did you
"Get
see him
Biden
say that?
somewhere."
Was that taken out of context, or did he actually
Yeah,
say that?
probably.
Yeah, I think it was taken out of context
The
because even he isn't that stupid.
The Franklin Project took
He
this
said it.
statement
Jamie
by
says he said it.
Trump and added one more to it. Promise?
What's that, Moshe? We can't hear you.
The Franklin Project took this statement by Trump,
Yeah.
where if he loses the election, he will leave the country, and they added one more word to it. Promise?
Yeah, promise.
You know something? If any ordinary person, like any one of us, said the things that he says in public, we would be committed to a mental institution.
Yeah.
You know, his niece, who knows him as well as anybody, his niece is a clinical psychologist. And she basically has analyzed him. And it comes from the family. And I grew up in Brooklyn. That's where they ran their business, in Brooklyn. And his father was a psychopath, like his niece said. And her father committed suicide because of the grandfather. In other words, Trump's older brother, who was supposed to inherit the
Right.
business, essentially drank himself to death because he couldn't deal with the father. And Trump is, you know, the spitting image of his father. They're both, well, maybe psychopath is too strong, but they're certainly sociopaths, and they've been clinically analyzed as that.
Yeah.
Um,
What makes Trump even more dangerous than his father or whatever is that, like, whenever I hear about the father, it just seems very kind of like a scary guy or whatever. Trump's scary, but his like, evil power is that he's like kind of funny. Like, you know what I mean? It's like he'll be saying shit, you'll like laugh out of a kind of nervousness. Like, you know what I mean? Like, because it's just so fucking ridiculous.
well, there are plenty of funny things that crazy people say,
Exactly.
but it's not a
Whenever I see
laughing
pictures
matter.
of the dad, he seemed kind of like dour and like.
The difference between him and his father is that his father never ran for public office, because in those days you couldn't get elected. And he basically came through a protest vote. It was a protest vote because he's I'm not going to say he's not the problem. He is the problem, but he is symptomatic of a much larger problem. The politicians of both parties have neglected the working class in this country for decades. And the political system is just rife with corruption. And if that doesn't change, and it's not going to change in my lifetime, that's for sure. But I don't give a damn, because I could leave the country.
Yeah.
I'm retired. I could leave the country. I don't have to be here.
My passport.
You know, the first thing let me tell you something. The first thing I did the day after he was elected in 16, the first thing I did was renew my passport.
Yeah,
I was scared shit. But you know something? It's not so easy to leave the country. What's the most logical place to go? Canada. You know, the border is closed.
Yeah, right. Well, that's the other thing now. Yeah, totally. It's like you can't even leave if you wanted to.
I don't know if you guys saw this miniseries on television, The Plot Against America, which was an adaptation.
Yeah, totally. Yeah, that was great.
Before I continue, Michael, let me stop you for a minute here.
You can go to Israel. I don't want to go to Israel.
If you want to leave the country, please let me know. I will help you. Mimi, I will help you materially, on one condition. I get your apartment.
Well, I mean, you know, most of us could go to Israel. Most of us could go to Israel.
You can go
But if you
wherever
think
you
Israel's
want.
any different from this country,
You can go wherever you want. I will buy you the plane ticket if I can get your apartment.
Believe me, I can afford the plane ticket. But the thing is, if you saw that miniseries, there was so many and Philip Roth, who wrote the book, is dead. He's been dead for several years. I think he died before Trump was elected. But he wrote an alternative history of Charles Lindbergh, who was a Nazi sympathizer, had run against Roosevelt in the 1940 election and was elected, what this would mean for democracy in this country. And I remember the Jewish theater manager where the protagonist in the story used to go to see films was encouraging the protagonist to get the hell out of this country, go to Canada. He said, I'm taking my family to Canada. Well, ultimately,
By the way,
they closed the border. They closed the border to Canada, and the Jews couldn't get out, couldn't go to Canada.
by the way, in this miniseries,
Yeah.
the temple that they show is our temple in Jersey City. That's my temple. That's where I go.
Oh, really?
Yeah.
So do you have an Italian-American rabbi, John Turturro?
Yeah.
Who's married to a Jewish woman. So that's John Turturro always plays Jews for some reason. Barton Fink, and in the quiz show, Herb Stempel, which was a true story. He always plays Jews.
Yeah,
But he probably grew up in a Jewish neighborhood in Brooklyn. That's what he knows how to. But it was so when I heard that Trudeau closed the Canadian border, I was shocked. Of course, they closed it because of the high infection rate in the United States. They didn't want the infection spreading. But I went back to that book, The Plot Against America. That's exactly what happened. So
yeah, you just got to marry a Canadian, and then you can get.
I don't think that would help. Well, in the old days, if you married an American, you could come to this country. But they've done away with that. They've done away with family.
One of my friends' sisters married a Canadian, and they actually have been to Canada since the pandemic. But they had to quarantine for like 2 weeks upon getting there.
Sure, but now you can't get into Canada unless you can sneak across the border. There's somebody who owns a house in Vermont that straddles the border.
Yeah, you can do it.
So if you can bribe the guy who owns the house, let you in the front door and leave through the back. Well, you can sneak into Canada. The border is not that secure. I don't know what you do after you sneak in, but but your passport's no good in Canada.
Guys, it's been real, but I think I gotta go.
Yeah. Okay.
But
excellent little after party that we had here.
One last comment, Matt.
Yeah.
Thank you for another delightful session.
Oh, thank you. Thank you for coming, as always.
Really appreciate.
Thanks, Matt. Now we're going to go and spend the rest of the night trying to figure out what you actually said.
The notes are online.
Got it. Yeah, well, I'm gonna read that paper, both papers.
It was so great that I'm almost willing to forgive you for skipping one session.
Yeah, well, we'll definitely do one next week. Yeah, and please, yeah, definitely, you can have some time, talk about your thing, and I'll review the Majorana stuff as well.
So Moshe, you're going to do faster than light communication at this?
No, just show that entanglement does not violate special relativity.
All right, but Sid is probably going to take up 2 sessions. I think tomorrow.
Yeah.
He's going to do an introduction tomorrow. If you're interested in magnetic monopoles.
Oh yeah, I saw that. Yeah.
Tomorrow, 1:00.
I'm often busy like Sunday afternoons.
Sid is very smart. He taught us Lie groups. He is very smart. And Lie groups are indispensable. I had never heard of Lie groups. Lie groups are indispensable in understanding particle physics.
Yeah, I love a good Lie group. I read there's a funny thing I read online where like some what was it? You know, some government bureaucrats saw Lie groups somewhere and was like, lie groups? What are you academics studying lie groups for? We're gonna like cut your funding.
Well, Lee is a fairly common Swedish name.
Yeah.
The first Secretary General of the UN was named Lee, Trygve Lee. I happen to know that. So
Was he
Lee is not an uncommon Scandinavian name. But Sophus Lee is, Lee. I don't know if he's related to Trygve Lee. Remember Trygve Lee, Moshe?
Vaguely, yes.
He was the secretary. He was the first Secretary General. They had to appoint somebody from a neutral country. Then ultimately they appointed a Nazi, Kurt Waldheim from Austria, and it turned out he had been a Nazi.
Yeah.
So they said, you heard of Alzheimer's disease? There's something called Waldheimer's disease. He had forgotten that he was a Nazi. One of the secretaries general of UN, Kurt Waldheim, had been a Nazi during World War II. Nobody knew it.
Crazy. All right,
Thanks,
guys.
Matt.
It's been real. See y'all later. Adios.